Hi, I'm Brian Amrine with Value Driven Analytics, and in today's training session, I'll start by providing a little bit of context around Python, followed by how to download it for free, and then show you how to perform all kinds of data manipulation using a weather data set. Have you ever heard anyone say it's been a hot April or a wet November? Well, today we'll build a weather seasonality index that can help us truly assess whether the weather's actually been different from the typical seasonality we've seen in the past. Oh, and we'll learn a little Python data manipulation along the way as well. By the end of this session, you should have a solid foundation for building and manipulating data tables that you can build on from there to perform more advanced automation and data science use cases if desired. If that sounds good to you, let's get started. When it comes to analytics, it's good to know Excel for quick analysis and financial forecasting models. You need to know Power BI or Tableau, an interactive visualization tool. And it's also good to know SQL for basic data manipulation. This is the common language that almost every other analytics platform speaks. Now, SQL can probably do 80 to 90% of the data manipulation you'll need to do as an analyst. But when you need to do some advanced operations like pulling data from an API, or looping or iterating, or especially building a data science model, you need to know an advanced analytics language as well. I'm talking about Python, R, or SAS. And today, we'll be learning Python. Let's take a look at Google searches for Python analysis, R analysis, and SAS analysis over time since 2004. In blue here, what you'll see for Python is become more and more searched for proxy for its popularity over time. Well, R has been perhaps flat or so over the last 10 years, and SAS has been declining in popularity for a while now from a Google search perspective. I'll walk you through a few similarities and differences across these three popular advanced analytics platforms. SAS has been declining for a while. It has a not insignificant cost, whereas Python and R are open source and free. And so more and more companies have gradually switched from SAS to either R or Python. Now, R has typically been the statistician's choice SAS alternative. It's historically had more data science libraries available than Python did. Python has been the more computer scientist, the programmer's choice language. I'm talking in generalities here. And so as a result, a lot of the data science algorithms that were created in Python were set up from the get-go to be very computationally efficient, very well able to run on big data sets. And what's happened over time is Python's data science libraries have become more and more popular. There's more and more operations and models that have been built into it. And so at this point, a lot of data science is not just performed in R, but Python as well. Now, Python, as a general purpose language, is more flexible than R or SAS. It has the capability to build applications, video games, even websites, in addition to performing data analysis and models like SAS and R can also do. Outside of that, I find R and Python to be quite similar in a lot of ways, especially compared to SAS. They're both open source and free, and they both have this syntax that typically starts with the object's name, followed by an equal sign, followed by the object's definition, which we'll see many examples of in today's demo. Both R and Python are often coded out and ran in an integrated development environment, or IDE. For R, RStudio is probably the most popular IDE. And for Python, a Jupyter Notebook, which is what we'll use today, is one of the most popular IDEs. But there are many others as well. A Jupyter Notebook typically has multiple code cells, and the output for each code cell, such as tables, charts, and model output, appears directly under it, as we'll see many times today. Python and R also both leverage packages that are full of functions for various data manipulations and actions. For instance, in Python, the Pandas package is very popular for manipulating data tables. The stats models package is very popular for all kinds of statistical learning models like regression models. And the sklearn or scikit-learn package is very popular for machine learning applications. And there are many more packages as well for all kinds of other actions. Now, Anaconda is a very popular distribution of Python that contains the Python executor, some common Python packages, and the Jupyter Notebook IDE. All three of the things we've talked about so far. So that's what we'll download next. Well, here we are on anaconda.com, and what we'll want to do once we get to the home page, scroll down until you see this free download option. Click on that, and then you'll want to click on download. And after that, just proceed through the installation instructions. Now, after you've completed installing Anaconda, the next step is to go to valuedrivenanalytics.com. I'm here on this site now, and we're going to download a few files that we'll need for our demo. So go to Analytics Training and then Intro to Data Analytics. And once we're on this page, you'll want to scroll down and find our Introduction to Python page right here. Now there will be a few files you want to download here. One will be called Creating a Weather Seasonality Index.ipynb file. That's the file extension for a Jupyter Notebook. Then we'll also want to download the weather.csv file. Those are the two files you need to download from the site. And if you'd like more detailed instructions on how to download Anaconda and even try it out, there will be a PowerPoint here for downloading Anaconda as well. All right, hopefully you've downloaded the Jupyter Notebook. Hopefully you've downloaded the weather.csv file. I've got the weather.csv file open here in Excel just to explore it a little bit before we actually import it into our Jupyter Notebook. It's basically a data set with one row per date, and it represents weather in Raleigh. So we have 4 different columns representing 4 different weather types, so to speak, in the Raleigh, North Carolina area. It starts with January 1st, 1980, and I'll scroll all the way down and you'll see it goes through December 31st, 2022. That's our data set. I actually created this data set using a weather API in Python, and that Python code that I used to generate this file is included at the bottom of our Jupyter Notebook. We're gonna start by just importing these results from that, but you'll see within the Jupyter Notebook how you can actually create this perhaps for your city and for your custom time period. But if we look at our columns here, we've got, of course, a date identifier. We've got our average temperature for that day in Fahrenheit, our precipitation for that day in inches, our snow in inches, and our average wind speed in miles per hour. Now there are a few, as we'll see, a few cases where this information is missing and wasn't available for that day, but for the most part what we'll find is that it's generally these metrics are populated across this entire time period. Well, that's a little bit about the file. Let's actually get into Python so we can actually analyze this file. You've downloaded Anaconda, you've installed Anaconda, you've downloaded the Jupyter Notebook from the website and the weather.csv file from the website, and hopefully saved that in a particular folder that you're using for this training session. And now it's finally time to launch our Jupyter Notebook. That's the IDE that we're going to use to run our Python code. Now that you've downloaded and installed Anaconda, Jupyter will have been installed by default. So if you search for Jupyter, like this, Jupyter Notebook should come up, and I'm going to go ahead and click on that. What'll happen is you'll get this command line type prompt that comes up that says Jupyter Notebook. You want to leave that open for the entire session. Once you're done with the notebook that we'll ultimately look at here, which will automatically come up in your browser. Here we go. You can close that later, but for now, we need to keep that Jupyter terminal session open. This needs to stay open in the background. Close it after you're completely done. You've saved your work in the Jupyter screen in your browser, but keep it open for that entire session. Again, until this is closed. Now this is actually a mirror of your Windows screen. There is a way to change which directory it opens to, but this is a mirror of your Windows directory. I'm going to navigate to where I saved the Jupyter Notebook. And so wherever you download it from the website, wherever you save that .ipynb file, maybe the CSV file as well, navigate to that folder. I'll go ahead and do that here. Here we are. Now what you'll notice is their typical file has this file icon next to it, but a Jupyter Notebook, a .ipynb file, has a notebook icon next to it, telling you, making it very clear that that's a Jupyter Notebook, and you can see it's got the .ipynb extension too. Well, that's the one that you've hopefully downloaded, and that's the one we want to launch. Now, the Jupyter menu, you can actually create a brand new notebook if you wanted to right here by going to the top right and clicking New and then Python 3, and it'll open a brand new notebook. And what you'll notice, I think it'll give it a name of Untitled, and you could start your work fresh. So that's one way to do this, and you'll see it created a notebook right here. Now, if I wanted to delete that, I could right-click and I'd have the option to shut it down or delete it. Now, if you wanted to just restart the notebook, you could shut it down, which means this will no longer be green. Kind of convenient that it told us that it was green, it was open. And what you'll notice here is it wants us to restart. I'll do that. And then now let's come back over here. Oh, it's green again. Great. So we'll close out of this here, and I'll say leave. And then if I want to actually delete this, I can just click the delete button after check marking it. Just a little about Jupyter navigation. Now let's open our Jupyter Notebook file in question. I've already pre-written some code, and this is the way I tend to work, and I think a lot of other analysts prefer to work as well. It's going to be really hard to memorize all the different Python operations that you could possibly want to do. I like to start with sample code, and if I need additional code, I'll do a web search to find that. But you might consider setting up your own sample code. It could be a Jupyter Notebook or even an Excel file, where maybe each tab represents something like importing data from CSV, and you've got some sample code for that. How to import data from an Excel file, and that could be another tab in your Excel file, and you've got basically a tab for every single Python data manipulation task that you'd frequently do. A pretty good reference, and eventually some of these things you may come to memorize and not need that reference document. But we're going to start with creating a weather seasonality index. So I'll go ahead and just simply click on that, and just like when we created a new notebook before, it's going to launch in a new browser window. One more thing I'll comment on, if you had any issues launching your Jupyter Notebook, sometimes, in fact often, if your browser is not Chrome, you could run into issues. A quick way to handle that, probably not the only way to handle that, would be to download Chrome and set it as your default browser, and then try relaunching again. In some cases, you might need to restart your computer. And if you continue to have issues, feel free to leave a comment, and I'll do my best to help you work through that. Well, here's our Jupyter Notebook. This is a Jupyter Notebook called Create a Weather Seasonality Index. And the very first thing, the very first code cell we have here is, or I should say cell, is not a code cell at all. It's a markdown cell. You can see the cell type right here, markdown. I can change this to a code cell like some of these others, and you see it has a similar format now, or I can change it to markdown. And I can run that by highlighting within the cell and click run, and then it kind of solidifies it as a markdown title. As you can see, this is a code cell. I'm just clicking into this. This is code cell and so forth. These markdown cells tend to be used for titles. I'll add another code cell or cell in general here by clicking plus, and whatever one I'm currently clicked in, you can see how it gets selected in blue or in green. If I click plus, it's going to put that cell directly under that code cell that was highlighted. Then if I want to move this from there, I can click this up or down arrow. So I'll put one right here, and by default it's going to be a code cell. So I could write some code here, or if I wanted to make it some markdown text, I might say just a simple title there. I'll change it to markdown, and then I can either run this, or let me go back to code here. A shortcut for running code, this is a great thing to know, is holding down Shift and then Enter and then letting go of both keys. Shift Enter. That'll do the same as running this essentially. Now I ran this as code, and so it gave an error because it's not good code. It's not actually effective Python code, but I'll change it to markdown and then it'll let me save it. Now notice how this is a lot smaller font than this is. A very quick way to change your markdown font size, let me double click on this again to go into it, is to put a hashtag in front of it. Watch what happens when I put one hashtag before it. There you go, it's the same size as this because this had a hashtag in front of it as well. Watch what happens when I put two hashtags in front of it. It's a little smaller, and you get the idea. So that's how to use, if you wanted to use titles, you can use markdown titles in that way. And that can be effective. Now another way of having titles and comments and such is to actually include comments within a code cell, and you'll see lots of examples of that right here. Now before we do that, let me show you, let's say I want to remove this now. So I added a code cell by clicking the plus button, and I can remove one. I want to select the code cell that I want to remove, that's important, and I'll click the scissors here and that will remove it. So I want to remove that one as well. Perfect. And let me go ahead and execute this so it actually looks like a title. Perfect. So anything that starts with a hashtag and the rest of that line after that hashtag is going to be considered to be commented out. What's a comment? A comment is text that is not actually going to be ran. Well, if it's not going to be run, why would you put it there? Comments are great to include in your SQL code, in your Python code, in all kinds of code. I don't know if there's anything a developer or an analyst dislikes more than inheriting code that doesn't have any comments in it. It can be quite frustrating. The comments are there to let, it could be someone else, but it could also be yourself coming back to a project maybe a few months later wondering, why did I set it up this way? Well, leave a comment that intuitively walks through what the code is trying to do, and that can help really speed up the time it takes to understand your code. Comments are a great thing. Now, some people might leave a comment above every single line to explain every single line. Others maybe every few lines and explain in general what this section does. Either way, add a decent number of comments to help yourself and others understand your code. Again, this is a code cell that we're in, and one of the first things we're going to do here is import two packages that we'll use throughout our Jupyter Notebook here, and that is the Pandas package. Remember we talked about that's a very common package for data manipulation. So in order to import a Pandas package, and the Pandas package is so popular that it was included in the Anaconda distribution. Remember, it includes the Python executor, so if you've downloaded Anaconda, you've got that. You've got quite a few popular Python packages, including Pandas, and I believe matplotlib should be installed by default as well, and several others that are very popular. You don't have to worry about installing those because they were included when you downloaded Anaconda. And Jupyter itself, the IDE we're using right now, is also downloaded. So these are already technically installed on your machine, in your Python instance. But we need, at the beginning of a Jupyter Notebook, or really we could import them anywhere. It's very common to import them at the top of your Jupyter Notebook. We need to import those packages that we're actually going to use in this Jupyter Notebook. We wouldn't import all 100 or so packages that Anaconda downloaded, only the ones that we need for this Jupyter Notebook. So we're importing pandas, and we just start with, you can see it's highlighted in green as a keyword here, import, and you put whatever package name you're looking for. In this case, it's pandas. In the next line, it's matplot.lib, and then there's kind of a library within that called pyplot that we're specifically importing in the second line. And you can see as is highlighted, that's another Python keyword. And as allows us to give pandas a shortcut name or alias. Same concept as table aliases in SQL, except this is for a package. So now instead of referring to pandas whenever we want to use a pandas function, we can simply refer to as PD. And whenever referring to matplotlib, and specifically the pyplot module, we can simply refer to PLT because we've set that as an alias. So this would work just fine to not have this as PD, but now we wouldn't be able to refer to pandas as PD. We'd have to spell out pandas. So that's what's going on there. A few examples of importing packages, and you want to import any packages that we're going to be using. Again, a lot of times at the top of your code, but it doesn't have to be. Now, if I want to run this again, you can either highlight that cell, click run, or use the keyboard shortcut, shift, enter, and then let go of both. And you can see for a little bit there, I'll do it again, it had a star next to it. Let me show you that again. A star. Oh, it was too quick. But it had a star here, and that shows you that that code cell is running or waiting to be ran. Now, it has a 3 next to it right now. This means that this code cell was the third thing that was run since I've opened this Jupyter Notebook. So if I run this again, now this is the 4th thing I've run, and if I run this, it'll have a 5 next to it. It has this number left over from the last time I ran this Jupyter Notebook. All right, so that's what the number's all about. The next thing we're going to want to do is set a variable, and Python is an object-oriented language. There's lots of different types of objects in Python. We're going to talk about some of the most popular ones that I personally use for data analysis. And the first one, a very basic one, foundational, is a variable. And you can have all kinds of variables of different types. For instance, float, that could have a decimal, integer, date, simple text, or really object is kind of like a text variable. And that's what we'll be setting down here is an actual text variable. And the concept of setting objects is very similar. The way you create an object in Python, regardless of whether you're creating a variable like we're doing in this case, or other types of objects, we're going to talk about list, Pandas DataFrames, potentially others. But the way you create all of those and the way you update them is very similar in terms of there's a left side, which in this case is path. That's the name of the object. You can give an object any name. You just need to be consistent when you reference that name later. So in this case, I'm calling this path. I could have called it anything. And that's the object name. Then, after the object name, regardless of what kind of object you're creating, there will be an equal sign. And then after the equal sign is some kind of a definition of that object. For a text variable like what we're doing here, it's quotes and then a lot of text. Furthermore, let me walk you through this a little bit deeper. I'm using single quotes here, which is fine. You just need to make sure you have a single quote at the end. You wouldn't want to mix and match a single quote and a double quote. But if I wanted to, this could have been a double quote, and I would just need to use a double quote at the end. And then that tells Python that anything within that double quote is the text that we want to set to this path variable. You'll see I simply created a path here. This is something you'll want to update. You'll want to update this to the path wherever you saved the file. Now don't include the file name here. It's just the folder, the path to the folder where your weather.csv file is located. There's also this R in front of it. This kind of tells Python to consider the text within those quotes literally. what'll happen is, especially with these backslashes, it will consider these to be escape characters. And so it won't consider the slashes. It'll maybe ignore this U, for instance. Backslashes are often seen as escape characters in Python. So there's a few options. I technically wouldn't need this R here if I were to change all of my backslashes to forward slashes. See here, that should work. I've got a few of them that I need to change here. That could work, but an easier option is to simply put an R in front of it, which tells it to kind of ignore those escape characters. So just update your path within the quotes here. You don't need to change the single quotes to double quotes. I just did that as an example. And then run this. So do Shift Enter. Now notice so far, this first code cell, this second code cell, there's been no output underneath it, right? Did we actually run it? Yeah, we ran it. We saw that it updated. There's no error messages. If there was an error, it would pop up an error message below the code cell. But we also didn't tell it to output anything. We didn't tell it to print or display anything so far. So we've set a path. We created our first Python object, and it was a variable object, path, which is simply equal to this. Now what we're doing here is we're setting a parameter at the top of our code, and that's another thing you want to set at the top of your code. You want to import your packages, and you want to set parameters at the top of your code. That way, if you need to move this this folder where all of your Python training session materials are, you can simply go to the top of your code and easily update the path there. It's not buried throughout the code. And we're actually going to use this path multiple times. And by defining it in a variable called path, we can simply reference path throughout the code. And if we ever need to update it, that path, we update it one place at the top of our code, and everywhere else where path is referenced doesn't need an update. It's just going to use the new path. So that's a really good benefit of setting variables at the top of your code. It applies to SQL in some cases. It can apply to Excel, even the same concept where you set parameters maybe in the top left of your worksheet. And as you change those, they're referenced multiple times in other coding cells, but they all reference those parameters, those cells. And so you change it there, everything else updates. This parameterization concept is a very useful one. All right, well, in the next code cell here, we're creating another object. Notice the similarity here. It's a different name. If we were to call this path, it would overwrite the path we set up here. So we're calling this object weather, followed by an equal sign. That is how you define an object in Python, regardless of what kind of object it is. But in this case, it's not going to be a simple text string. It's not going to be text within quotes. This case, we're going to define a Pandas DataFrame on the right side. And in this case, we're referring to PD. Hopefully that looks familiar. If we scroll up here, you'll notice we gave Pandas an alias of PD. And so if we hadn't done that, we could spell this out as Pandas. But we have an alias there, so we'll reference that. And then we're doing dot. It says from the Pandas library, dot, we want to use the read CSV function. And that function, similar to functions in Excel and SQL, it starts with an open parentheses and it's going to take some arguments. In this case, the argument we need to have there is what is the path to the CSV file you want us to import. That's the argument that this function takes. Notice this as well. We're referring to path. Well, how does it know what path is? Well, we set it in the code cell above. We could set it anywhere. We could set it, we could have actually consolidated this into one coding cell and just put this right here, for instance. That's fine. We can have multiple lines of code being ran in the same code cell, as many as you want. It's kind of an organization tool, so maybe you'd use one coding cell for a certain section operation, set of operations, and then you use a new coding cell for something that builds upon that, perhaps. Lots of different organization layers here. But that is essentially the definition of a Pandas DataFrame. This path has a CSV file. I want you to use the read CSV function from the Pandas package and take that to create a Pandas DataFrame and call it weather. Now we haven't told it to display anything yet, so it's not going to display anything, but by running this code cell, I'll go ahead and do that now. Now another object has been created in Python. It's called weather, and it's a Pandas DataFrame object, which we'll see is kind of like a data table. It's like an Excel worksheet with rows and columns. We'll eventually print it out and see what that looks like. Here's an example of how to print. You can print any object in Python. It doesn't always, especially when it comes to Pandas data frames, we'll see there's a better way to display a Pandas data frame than using the print function. But print works great for printing variables. Path is a variable that simply contains text, and if we want to show and see what's in a particular variable, we can simply run print and then name the variable in the open parentheses. And there we go, which is exactly what we set it to. So it's showing us that path equals this big long path that we set. Now, let's say we said, okay, we printed path. And this time we're trying to print path, but we used a capital P. Well, Python is case sensitive. Path with a capital P is different from path than a lowercase p. So if I run this, I'm going to get an error because it says path is not defined. We had to define path with a lowercase p, and we did. We already set it. We set it up here. Remember, we gave it a name. Path lowercase p equals this, and so when we printed it, it printed that exact value that we set it to here. Very straightforward. But when we try to print something that we haven't set path with a capital P, Python is case sensitive, it gives us that error. And it's a pretty straightforward error in this case. Path is not defined. Now I'll just go ahead and walk you through when there's an error message. There are just a couple parts that I really focus on. One, especially if you have a lot of lines in your code cell. In this case, there's really one line that's being ran that's not commented out because of the hashtag here. It's very straightforward. That's the only line of code, so that must be the thing that errored out. But what if you had a code cell with a lot of different lines in it? It's very helpful to see right here that it errored out on line 5. So that's helpful when it points to the line where it errored out on. And then the last part here where it tells you what the error actually is. This is very helpful as well. And what I might do from here is potentially take this and do a web search for it and see if I can find a good article to explain why I got that error, maybe a way to correct it. Let me do that here. All right, now there's one more thing that I would recommend changing here. This path is kind of a custom thing. I called it path. It's not something that probably other people are necessarily using. And so I would remove any parts of the code that are really specific to your use case. In this case, the name path, I set that name. A lot of other people might use another name. And so I'm going to remove that. I'll probably get better results that way. And you could look at the first result you get. Stack Overflow is usually good, and looking at the first accepted response is usually good. In this case, it's actually telling me right here, it's raised when the program attempts to access or use a variable that has not been defined. That's exactly what happened here. We just defined lowercase p path, and so we were able to print it with no problem. We again defined it up here, but we did not define uppercase p path, and so it gave us that exact error. There you go. All right, well, let's try printing weather now. Remember, weather's a different type of object. Path, lowercase p path, was a variable object. Weather was defined as a Pandas DataFrame object. Let's see what happens when we try to use the print function on that. It absolutely works. Here's our column titles. Remember when we took a quick look at it in Excel, the weather.csv file? You can see the similarities here. It's got those 5 columns. Now it had to go to the next line and put your last 2 columns on the next line. That's not very helpful. You'll see that it's showing you the first 5 rows and the last 5 rows. It's got an extra kind of a column here. This is called an index. It shows you, and Python starts everything with 0. It shows you your first 5 rows, your last 5 rows, and so forth. And it tells us even how many rows and how many columns are in it down here. So that's what happens when you print a Pandas data frame, but there's a nicer looking format. It's considered an HTML format that you can get for a Pandas data frame when you use the display function. And that's what we'll do down here. Let's take a look at our weather data frame when we just use the display function around it. Ooh, that's a little nicer. All of our columns are on the same line. If we had even more columns, we'd have a scroll bar where we could just keep scrolling and see all of our columns. Sometimes there gets put a dot in between it if you have too many columns. And that's a setting that you can set to show as many columns as you'd like it to. Now it'll use more and more memory if you have a ton of columns, and it could be too much for your computer to handle at a certain point. You'll notice, similar to the print function here, it's still showing us the first 5 rows and the last 5 rows in the Pandas data frame, but it's really clean, and you've got the alternate color of the rows here, which is nice. A lot cleaner than using print is, so I highly recommend using display to actually view what your Pandas data frame is. And it's good to frequently use this to monitor after every data manipulation. How does my Pandas data frame look now? Did it create the column like I expected it to, or update the data frame like I expected it to? And we'll see more examples of that. Now, if you wanted to see more than just, say, the first 5 and the last 5 rows, you could use a few other operations. The first one we're going to show here is the .head function. We're still using display, but we're nesting this .head, and then it takes an argument n equals a number. In this case, n equals 20. .head means I want the first X number of rows shown. In this case, n equals 20, so it's showing me the first 20 rows, and 0 through 19, which ends up being 20 rows, right? I can run that and see that. Now you can also use, if you wanted the last 12 rows, we could instead do tail, and maybe we want to see 10 items instead. There you go, last 10 items. So we're using tail to accomplish that, and we just updated the n equals as well. Another way that you could handle this, if you wanted the number of rows shown to be changed for every Pandas data frame going forward, whenever you display a Pandas data frame, I want to see, in this case, we're setting it to 50. You can change the min rows setting using this code right here. And now what you'll notice is when we just simply display weather, before we got the first 5 rows and the last 5 rows, now it's going to show us the first 25 rows and the last 25 rows. So I'll set it back to 10, which is the default, and then it'll show me just the first 5 and the last 5 again. All right, there's another way of displaying something. In fact, I used it right here. Notice this time I didn't actually put display around weather at all, but it displayed the data frame. Why didn't it give us an error? Why did it display it in the first place? Well, whenever you put the name of an object, it could be a variable like path or a Pandas data frame or any kind of other Python object, whenever you list it as the last thing in a Jupyter Notebook. So this is a Jupyter thing. Whenever you list it as the last thing in a Jupyter Notebook coding cell like it is here, it'll display that. So in this case, weather is the last thing, and so it shows it. But it's got to be the last thing in that code cell. Watch what happens when I put weather here. I didn't put anything around it, I just put weather. But then there's another line after it. In this case, I'm creating another text variable called another line, and it equals test, which, so the definition of this is a text variable. It's very similar to what I did with path before, but the point of this is that there's a line after weather now. Weather is not the last line in the code cell. Well, now it's not being displayed. Yes, because weather was not the last thing displayed there. And it's not displaying another line either, because there's an operation happening here. A object is being updated because of the equal sign, or created in this case. But if I just listed another line, in fact, if I put another line as by itself without updating anything, there's no equal sign here. Now, another line is the value that another line equals is being displayed. wanted to show some examples around that. Hopefully it's starting to make sense just to solidify that a little bit more, and show you what if I wanted to display weather, but I didn't want to include it as the last thing in the code. So how do I do that? Well, you can always put the word display around it. Actually, specifically put weather in a display function, and it doesn't matter whether it's first or middle or last of your code cell, it's going to display that. You've explicitly told it. It's just that the shortcut of not having to put display around something to display it, that only works when that's the last thing in the coding cell. So if I put display around weather in this case, it's going to display it just like it did before. We showed how to import our CSV file into a Pandas data frame. We did the pd.readCSV. And there's other ways to import data as well. In that same code cell above, I showed an example. I'll just scroll up to it. I have an example here of importing another Pandas function, read Excel. And in this case, we're still specifying path like we did before, but we're pointing to an Excel file instead, an XLSX file. And an Excel file can have multiple sheets, unlike a CSV file. So when you're importing an Excel file into Pandas, you've got to specify a sheet name. So you can use this as example code if you have that use case of importing an Excel file into Pandas. But I would say that the most common way, and probably the best way to import data into Python, if possible, if you have access to a database, is import it via SQL query and import that directly into a Pandas data frame. And the syntax that you would use to import that SQL query and the results of that SQL query into a Pandas data frame is going to be different depending on the SQL database you're using. So it's best to do a web search for that. And if you have any questions or would like me to try to provide some sample code for that, feel free to leave a comment and I'll do my best to help you out with that as well. All kinds of ways to import data into Python. Now, one of those ways, I'll scroll back down to where we were before. One of those ways, every now and then, this comes into play, you might want to manually create perhaps a small data frame. In this case, we're using another Pandas function. That's why we started with PD, the alias we gave to Pandas. And we're using the data frame function. And so there's some open parentheses, open brackets. This is really hard to memorize. Maybe you get there eventually if you do it enough. But for now, this is one of those things you want to stow away in a sample Jupyter notebook like this one to reference later, or you could look it up on the spot, do a web search for how to create a Pandas data frame manually. Or maybe use Excel for it. And there's a tab in your reference Excel workbook that's how to create a Pandas data frame manually, and you copy this code for that. But what you'll see here is we're naming a different column. There's 3 columns here: weekday, hour, visitor, and we show what we want, the weekday column to have for the first row, Monday, and then second row will have Tuesday, and first value for hour will be 12, and then second value for hour will be 12 again. Visitors will have 5 in the first row and 8 in the second row. And when we and then we create an index here, 0, 1, 2, 3. In this case, it only has 2 rows, 3 columns, and then we display that Pandas data frame that we've created manually, and there it is. We've created Pandas data frame manually. Pretty neat. Well, that's a Pandas data frame, and you can see how we've referenced a Pandas data frame. We simply reference the name of it. In this case, row was the name we gave to it, so we displayed row. Well, what if you wanted to reference, look at, or update a specific item of a data frame? And in particular, a data frame is a set of columns. What if we wanted to call out a specific column within that Pandas data frame? Well, you simply list the data frame name. So let's go back to our weather one. And then you do an open bracket. Now, there's actually a few ways of doing this. You may occasionally see it done this way. I guess you might call that dot notation. But maybe more common is to use the open bracket quote. This could be a single quote or a double quote, as long as it's consistent. So if I use a single quote here, I need to use a single quote here. And then a name. And what's nice about this is if you had something date space, if it had a space or a special character in it, the dot notation would not work. But this works even if you have a space. You put whatever that column name is within the quotes and it's fine. And then of course another quote to close off the first quote and another close bracket to close off the open bracket. So our column name was date. So we do data frame name, which is weather. And here we want to call out and specifically reference the date field. So that's how it's done. And if I run this, again, it's the last item in the coding cell. And so that's an easy way to get it to display, or we could specifically put display around it. That would work too. We just see the date column, right? There it is. The first 5 rows, the last 5 rows, similar to before. When it's just a column, it takes it out of that HTML format, so that is one difference. If we wanted to reference multiple, multiple columns, we can do that too. What we would do here is just put two brackets. So open bracket, and it's going to try to close this off. You have to look out for that. Open bracket, and then you would list all of your columns here, separated by commas, with quotes around each column. So date and average temperature, if we just wanted to show those two, that's how we can do that. It's limited that data set just to those 2 columns we referenced. And you need the double brackets in order to accomplish that. And just whatever columns you wanted separated by commas. If we wanted to add another one, we would just add comma, and then we'd put another column within quotes. And then we'd have a third one included. So maybe I want to include snow as well. Another neat thing about this is a great way to change the order of the columns as well. Let's say I wanted to have snow as my first column. It's going to display these in whatever order I put them in. So now I'll put snow first, then date, then temperature. I don't know why we want to do that, but just for fun. An error. Let's see what happened here. Snow inches is not in index. Now notice this. So row 4, it tells me that this was the error, and I'm looking at this and I'm saying snow inches. It's missing a closed parentheses, and so I will add that. Yeah, especially if we reference like down here, we can see that snow has a closed parentheses on it, and we'll run that. Now we have snow first, and then the date, and then average temperature. So it shows you how you can select just specific columns and how you can reorder those columns. Now, we haven't updated anything. We have not overwritten weather. There is no equal sign here, and so we haven't updated anything. We're simply displaying it. And again, because this is the last item in the code cell, technically we don't even have to put display around it. We're just looking at the data frame, these 3 columns, in this particular column order. We haven't updated anything. Now we're actually going to add a column to our weather data set. And this is a really simple column. It simply equals test value for every single row. Well, the way you do that, again, we're referencing the column on the left side. So in this case, we're not updating the entire Pandas data frame entirely. We're not overwriting the whole thing. We're just updating a certain column. Whether we're updating a column that already exists or adding one, this is the way you'd set it up, where you reference the Pandas data frame name and the column name using the bracket and quote as we looked at before. So we have effectively referenced a column here. If test already existed in the data set, if I, for instance, if I changed this to date, this would overwrite the date with whatever definition is on the right side. But in this case, if I reference something that doesn't exist in the data frame, it'll simply add a column called test. It's that simple. If the column already exists, it'll overwrite it. And if it doesn't exist, it'll add a new column. And we'll see exactly what happens right here. It added a new column, and the value is always test value. Just a real quick way of showing you how to create a new column. Now, what if we wanted to create something more sophisticated here? Let's say we wanted to create another column. Well, here we're going to overwrite test. So this is another example. See how it doesn't create another test column. It overwrites test in this case. Same variable test, but this time, instead of it just being a single value, we're going to reference another pandas column, in this case temperature, and we're going to add one to it. Just an example of how you can use another column as your starting point, and we could multiply two columns by together, add two columns together. In this case, we're just adding the same number, 1, to whatever that row's value was for average temperature. And sure enough, here's test. It's always 1 higher than whatever the average temperature was for that row. A very popular way to create new columns is with kind of like if logic, the same kind of if statement that you'd use in Excel. This is similar to a case when statement in SQL, where based on a certain criteria, I want it to equal this value. But if that's not true, then if it's this criteria, then have it set this value, and on and on and on. You can nest a lot of if statements in Excel. You can have a lot of when statements in SQL, and a case when statement. Well, what we're going to use is the numpy package, and we're going to give it an alias of np. So normally we would import this at the top. I just decided to show it here because this is the first place where we're using numpy in this case. But what you'll notice is we're going to reference the numpy function package, and we're going to pull out of it the where function. And it takes 3 arguments exactly like the if statement in Excel. There's going to be a condition. In this case, if this column, average temperature from the weather pandas data frame, just like we've been referencing columns, if it's less than 35, very similar to Excel, then a comma. So that's our first argument, is a condition, just like the if statement in Excel. Second argument, if that condition is true, if the temperature is less than 35, what do you want this column that we're defining, in this case we're calling it test, to equal? Just like the if statement in Excel. Cold, in this case we'll say if it's less than 35 degrees, we want it to have a value of cold. And because it's a text variable, all text variables, if it's going to have some text in it, it needs to have either double quotes or single quotes around it. So we have that here. If it was just going to be a number variable like 1, then we wouldn't need quotes around it. And then in this case, you don't have to do this, but in this case, we're nesting np.where statements. We could just simply say otherwise hot, and then close it off. That would be valid if we wouldn't want the rest of it at that point. But what we're going to do here is nest what we want the value to be if that's not true. So the if statement, the np.where statement, works the same as an if statement. Condition, what do you want the value to be if that condition is true? Comma, what do you want that condition to be if the value is false? If the value is false, if it's not less than 35 degrees, we want you to execute another np.where statement. We want you to check if the temperature is less than 55. And if it is, so at this point, the temperature would have to be 35 degrees or higher, because if it was lower than 35, it would already have stopped here and said the value is cold. But if it moved on and it found that maybe the value was 35 or 36 or 37 or anything up to basically 54.9999, then it would have a value of medium. Let's say, okay, well, this condition is true, and so we'll set the value to medium. And then if that weren't true, it would set the value to warm. You have to always make sure you're closing off parentheses, especially if it's nested like it is here. And what you'll see here is we've created another column. We've updated a column, same, because we called it test, and test already existed. And notice 37 degrees, that's medium. 34 degrees, that's cold, it's less than 35. And here's one that's above 55, and so the value is warm. Simple if logic using the numpy function, the where function. That can be quite useful. Well, we created this test column. We don't really need it, so let's delete it. And here's a simple statement for deleting a column. Setting a column and updating columns, we always had that left side definition, name of the object equals whatever the definition is. When you're deleting a column, it's just simple del. You can see that's a keyword space, and then you reference the column that you're trying to delete. So now if we do that, we'll see that weather no longer exists. And if I try to run this again, well, it should get an error message that no longer existed. Yeah, that it says key error test. A lot of times that means the object doesn't exist. The test column doesn't exist in this case. Now there's a concept, we've talked a little bit about this as it relates to variables of data types, the float data type, the integer data type, date data type, object data type. We also have that concept when we're dealing with Pandas data frames. In fact, each column within a Pandas data frame can have a different data type. So let me run this. We'll see there's our date variable is in object format. Our other variables are in float format, so they can have decimals. So those are our data types. There is a date data type, and so we may want to potentially convert date to a date data type so that the value of that would be, there's some specific date functions we can use within Pandas when a variable on a column that has specifically been set up as a date type. So the type that is assigned to a column can influence the type of functions that we can apply to that column. And notice to get all this, all we did was weather and then .dtypes. That was the function that we applied, and it showed us the data types. The next thing we're going to show as well is the .describe. This is a great way to get started with your Pandas data frame. For any of the quantitative fields like float 64, int 64, any of your numeric fields, so it's not going to work for object fields, and yeah, it's going to give you your summary statistics with .describe. And so it'll give you the count here. It'll give you the mean or the average, your standard deviation, minimum value, maximum value, and then your percentile values, 25th, 50th, 75th percentile values. So a great way to get to know your data. This data set's for Raleigh since 1980 through 2022. See the hottest day from an average temperature perspective. So this is not the high, is 90.7 degrees. Pretty hot day. Coldest was 4.3 degrees, pretty cold for Raleigh at least. But the average temperature, the average temperature across all the days was 60 degrees. Not bad. And then the count here represents not necessarily the number of rows in the data frame. This can be tricky. In this case, it's pretty close because there's not a lot of missing values. This is the number of non-null values. If you've never heard the term null before, it basically represents a value that's missing. It's not zero. Zero is considered to be not null. It's a value. But what if there was just nothing there? There wasn't a zero or any value at all in the column. That's called a null value. And missing data is a fact of reality. You don't always capture every piece of information for every single row. And so as a result, there can be some null values. So if I look at this, I'm seeing 15,651 non-null values for the average temperature column. And I'm noticing that precipitation and snow have 15,706 rows. So they have more non-null values than average temperature. And if we look at average wind speed too, it looks like there's 15,701 non-null average wind speed values, which means there's only, well, it looks like there's maybe 5 rows based on snow and precipitation having the same value here, maybe 5 rows where wind speed was missing. But it's possible that maybe there was some cases that precipitation and snow had missing data as well. What we can do to figure out how many rows are there actually in the whole data set, regardless of null values, I just want to know how many rows are in the data set. That's where the length the len function could come in. So I'm using this len function, putting the name of the Pandas data frame we're looking at, weather, and this is regardless of how many null values are, how many rows are there in the table, and there's 15,706. So I can compare that to this count to be able to say, okay, precipitation and snow, they don't have any null values. Now clearly they have a lot of zero values, but those are not null. They don't have any actually missing values in this data set. Average wind speed has about 5 rows missing with a missing 5 days with missing wind speed, And average temperature has about 55 rows missing there where the temperature wasn't available for that day for some reason. So that's a quick way to kind of assess that. Compare the length of the data frame, the full number of rows, to how many non-null values there were in that particular column, especially by using the .describe function here. Now you can also get what's called a list. This is another data type that we really have maybe seen, but we haven't talked about at this point. And one way to get a list of all the columns in your Pandas data frame is to just do weather.columns. Notice it looks a little different than when we did .d types. We technically got the column name and its data type. When we did .describe, we got the column, and we got some summary statistics. Here, let's say we just need to get the column names. We just want the column names. We need to do something with these column names. We don't want the extra stuff, the summary statistics. We just do the data frame dot columns, and it returns what's essentially kind of like a list. And so that list contains contains 5 items in this case because there were five columns in the data set, just the name of each column here. Now, another way of creating a list is to actually define it manually. So in this case, we got a list by extracting the columns from the weather pandas data frame, and that gave us a list of all the names of the columns. Well, if you want to define a list, you can simply do list, open parentheses, open bracket, and then put all the items in that list separated by commas. If it's numbers, similar to what we talked about with the np.where statement, if it's going to be a numeric variable, you don't need to put quotes around it. So in this case, it's a list of 5 numbers, and I can print that list just by doing the print function. And hey, it's another object, right? So it has a certain name. It's on the left side, equals, and in this case, the right side, it doesn't define a variable, a text variable like path did. It doesn't define a Pandas data frame like when we imported our CSV file using the pd.read CSV function. This is how you define a list, which means that custom list of numbers is going to be a list. So when we run that, we see that it's a list. Here's an example, custom list of words, and it's very similar to how we defined the list of numbers, but in this case, the things within the open parentheses, open bracket are words. And so they need to have quotes around each word. And what you'll see is we've got a list of words in this case. The only difference is we had letters and we put quotes around each item. If we don't include this and we have letters here, we're going to get an error. Just show that. So whenever you have text items, they need to have, again, either single quotes or double quotes around them. Yeah, didn't like that. Now, if we didn't have any text here, this would be fine. But it's not gonna have the text there. Hopefully that's helpful. I'll undo this here. All right, now another thing we can do is we can take that length function that we applied to our weather data frame, and we can apply that to a list. Remember, weather.columns returns a list that looks like this. And we defined a list of numbers here that have 5 numbers in it. And we also defined a list with 3 different words here called custom list of words. I'm going to print the length of each one of those. The length of a list just represents the number of items in that list, similar to how the length of a pandas data frame represented the number of rows in that data frame. So what you'll see if we run this is that there were 5 items in the weather.columns list. Yeah, it has 5 columns in other words. There were 5 items in the custom list of numbers, which is correct, and there were 3 items in the custom list of words. And I'm looking at these, and I know that the first thing it's going to print, because the first thing that's in the code cell is the number of columns. So it executes this, that's going to be the first thing that gets printed. Then it executes this, that's going to be the second thing that gets printed, and so forth. I want to show you another Python data type, and that is a set. A set is very similar to a list. It's a combination of items, a combination of variables. But a set cannot have any duplicates. So watch what happens when we get our custom list of words. Remember, I put two of the same word in there. Word one, put that in there twice. And then there was word two as well, which is a whole nother text, right? But there was one set of duplicates, word one and word one. When we convert that into a set, just by putting the set function around it, it will bring it down to 2 items, because a set cannot have any duplicates. If I wanted to turn that back into a list, I could simply put list around that. So you can, of course, nest things. Another thing you can do, technically, a pandas column is similar to a list. So if I took the pandas data frame weather and specifically the average temperature column from that, and I wanted to know how many rows there were, I believe this will get the total number of rows. This is not necessarily going to get just the non-null values. I can wrap length around that and get the number of values in that column. We can do a test to make sure that it doesn't include null values by maybe taking one of these columns like precipitation or actually average temperature. We know that that had about 55 null values, and so we can see that this has 15,706. It has more than the number of non-null values, 15,651, and so this is counting all of the rows, even if they have a null value, when you use this length function. Another thing you can do applied to a pandas column, in this case the temperature column, is you can get a unique list of all of the values. Turn that into a list with the .unique option. Now if I were to do .values here, and I believe it doesn't have a open parentheses, close parentheses, it would have the 15,706 values, all of them turned into values, turned into a list of values, duplicates and all. Again, 15,706 items, in this case decimals, float 64 data type items, and a list. But when I do .unique open parentheses, close parentheses, and apply that to a pandas data frame column, it'll only give me the unique values. So here's a list of all the unique values that are found. It's similar to like a select distinct in SQL, and similar to a drop duplicates in Excel. Now, what a lot of analysts end up doing in Python is applying a length function to that to find out how many unique values there are. So if we apply a length function around this, we can see that that represents 408 unique values within the average temperature column. Now let's talk about how to filter down your table. In Excel, you might use the filter operation, very easy. And in SQL, you'd probably use a where statement. But in Python, the way you want to filter down your data set is to simply have the pandas data frame that you want to filter on, in this case weather, and we'll do an open bracket, and then we're going to put a condition within that bracket. So this is a condition. We have to specify the column like we did before, where we have to specify the pandas data frame and then the open bracket, the open quote, just like we've been referencing columns. That remains the same. And then condition, in this case greater than 90, this is just going to return the rows that meet this condition. And there you go. You see that all 3 of these rows have a temperature above 90 degrees. Again, null values are cases when data is actually missing. We saw that there were about 55 null values for the temperature field, for instance. And if we wanted to filter down our data frame to just see those 55 null values, rows with null values, we can simply update, again, weather, open bracket, and then we've got a condition here. The way to reference null values, if you wanted to pull null values, is to use the .isNull, and this is going to pull all of your null values. And what you'll see them represented as here is is NaN. That's how Pandas represents null values. NaN, you can tell that it's missing there. These are populated, right? Even if they're 0, they're populated. These are populated, these are populated for average wind speed, but here's some cases where average wind speed was null that day as well. There we go, we see all the null values there. If you just wanted to pull non-null values, instead of doing .is null, you do .not null. Then there's so many that aren't null here that you're just seeing the first 5 and the last 5 shown. Now, here's another concept that I want to show you by looking at null and non-null values. Another way of getting the non-null values, remember how the way to get the values that are null is to use the .is null. But if you ever have a condition here, that you say, well, I actually want the values where that's not true. Another way of writing it is to put a tilde sign in front of the condition here. Now we have a tilde, so it's saying, here's the condition, and if I didn't have the tilde here, this would pull your null values, right? We said is null. But if you said, well, I want the rows where that condition is not true, another way, so we saw how we could just put not null, that would be fine. Not null, that would work just fine. But another way of handling that, there we go, is to put a tilde sign in front of it. And so this is saying, I want the cases where this variable is not null. And there you go, we get the same results before. There's so many that it's just showing us the first 5 rows and the last 5 rows. All right, let's say we want to do something a little bit more complex, where we wanted to just see rows that are either null or have a temperature, they're not null and they have a temperature greater than 90 degrees. You can use syntax like this, where what you have to do, and you could have as many of these as you wanted, you have to put each criteria, whether temperature is null is a criteria. You need to put parentheses around that. Notice how I have parentheses around this condition is null. And then I would need to separate that by either an and sign. If they both needed to be true, then I would have an and sign here. And if we needed to have an or sign, I'd use this pipe. And then notice this other condition is also enclosed in parentheses here. So this is going to say, I want to return it if the temperature is null or if this condition is met, if the temperature is greater than 90 degrees. See what happens here. See plenty of null values, and we should see 3 greater than 90 degree days there as well. There they are. Looks good. So here's an and example. If we wanted to find days that had the temperature below 10 degrees, but there was at least some snow, greater than 0 snow. Notice how we have the and sign between these, and our criteria are still in parentheses here. And now we get rows that meet both of those criteria. So that's how to handle this if you have multiple criteria that you want to consider, either or and criteria, similar to how you would use an and or and where statement in SQL. Now, the line below is actually going to create a new table. What we've done so far did not update the weather data frame. The weather data frame still has all the rows. We just filtered out some rows for displaying purposes. We didn't update anything. We didn't create a new data frame. If we actually want to create a new data frame, we need to have an object name and an equals. And we can have that same criteria we had before when we were looking at the greater than 90 day rows. But now we're going to add an object name and an equal sign before it to actually set it to a new object. In this case, weather above 90, or set it to an object at all, whether we're updating an object or not. So I'll go ahead and run this, and you'll see that now if I display weather above 90, it's an object now. It exists. We can reference it in other code cells. Or if we wanted to actually update that data frame and say, we're going to overwrite weather just with those greater than 90 degree days, we can run. The only difference here is now the left side equals an existing Pandas data frame. If we run this, it's going to overwrite weather, just like it overrided the test column within weather when we reference that on the left side. So now we do that, we display weather. There you go, weather only has 3 items now. Well, we actually want to see all the rows, so I'm just going to go ahead and re-import the weather data frame just like we did at the top. So I'll go ahead and run that. Now you'll be able to see it's brought in again. I'm going ahead and displaying the data types, and you can see the date. Again, it's an object data type, which is kind of used for strings, just simple text field, character field. Well, we're going to want to use some date functions against that column, and so I'm going to go ahead and convert it to date. To do that, I'm going to update that column, and so I'm going to name that column on the left side, reference that. Hey, it's from the weather data frame, it's called date, equals, here's what I want that to equal. We're gonna start with the weather date field, the same field we're updating, but we're gonna apply to it this pd.toDateTime, and it's gonna automatically try to detect what date that is. Now, if you have a really complex date, it may not be able to figure it out, but most of the time, this works just fine to convert it. And watch what happens now. When we display the weather.dtypes after that, scroll up here, it's now in this datetime64 format. So we have effectively converted it from an object data type to now the date column is in a datetime format. And what that's going to allow us to do is to create some more columns using these date functions that are only available, that can only be applied to date type columns within a Pandas data frame. The first one here is we're going to take that date field now, and we're going to do .dt. So we're referencing some date functions here, .dt, and we're going to extract the year, .year. And all that's going to do is notice we're updating a brand new column. Year doesn't exist yet. And if we look below, we'll go ahead and run this year. It just took the year from it. So we were able to take this date and extract the year part of it, which can be very helpful when maybe we wanted to group by year at a certain point. So now we've got just the year part. Another thing we can do is get the month part just by doing .dt.month. And as you can see, that takes out the month number, 1 for January, 2 for February, all the way through 12 for December. Another thing we can do, if we want just the month, the actual name of that month, not the number, maybe for formatting purposes, we think it'd look a little nicer to see the month name, we can instead say month_name, open parentheses, close parentheses, and that'll extract the actual full month name. Now within especially text variables, this works for text variables, but we can also apply these text functions to a text variable within Pandas. So we have this text variable now, full month name, and let's say we just wanted to have the first 3 characters, a shortened version of it. What we can do, because this is a string variable, an object variable, is we can, similar to kind of what we did here with the .dt, we're going to say .str. We want to use a string function in this case. And that function, we're going to start with these open brackets. It's really just referencing part of that string. Now, Python always starts with 0. So what's happening here is we have a colon. It's saying, don't start from the very beginning by default when it just has that colon there. If we wanted to start position 1, let's say, and then go through position 3, and the second number here is not inclusive, just some things you learn as you use Python, what's going to happen is it's going to skip the first character because Python starts at 0, so it sees the first character as position 0. It's going to include technically the second one, index of 1. It's going to include number 2. It's going to stop at 3 because that's what we included here. So watch what happens if we update it to be 1 through 3 eventually. Here, you get AN. Again, J would have been seen as the 0th item. A is 1, N is 2, and then it stops at 3 because this number here it's not inclusive of 3. If I want it to be inclusive of 3, I just update this to 4, and now you see we have A and U. We have position, essentially 1, 2, and 3 here, and J is position 0. And if we don't include anything here, and I update this to 3, it's going to be position 0, 1, and 2 is what it'll capture, which is what we want in this case. So now it got position, the very first one, position 0, which is J, position 1, which is A, position 2, which is N. And then again, stops at 3, not inclusive of 3. So that's how you can apply this text function to grab that. We can also even do, and then there's all kinds of things. We can add time to pandas dates. You could do a web search to figure out how to do that, or if you need to know how to do that, feel free to leave a comment as well. We can add time, we can subtract dates, all kinds of date manipulation you can do. But in this case, we're applying a lambda function here. This is something I copied online, but lambda functions, there's all kinds of cool things you can do with that. What we're doing here is taking the date and we're replacing the day part of it with 1. I ask, why would you want to do that? Well, this is a grouping mechanism. Let's say we want to keep the year part, we want to keep the month part, but we want to group all of the days within a month together into one row eventually, perhaps. Well, what happens here is now all, whether it's January 1st, January 2nd, 1980, January 3rd, they all have the value of January 1st, 1980. We've effectively grouped them all into having the same value of month start date. We haven't grouped them yet, but we've set it up so that they all have the same value within month start date. And similarly, all the values in December 2022, they all have the same value, December 1st, 2022. When we create this, you could call it month start date variable. Well, the next thing we're going to do is actually do some grouping. And here what we're getting ready to do is create a monthly seasonal index. Figure out how much higher on average is temperature in a particular month than the average for the year. And so in order to do that, we need to group, we've got days from 1980 to 2022. We want to group and look at the average temperature by month across that entire period to figure out, okay, what's the typical temperature in January, February, March. So what we're doing is we're going to group by month number. So one for January, 12 for December, everything in between. And we're going to take the average or the mean across this column, average temperature. And there's this really cool function, a pandas function called group by. So we're starting with the pandas DataFrame weather. We need to specify that. Then the group by function. And the way this works is it takes in, hey, what do you want to group by? We could group by multiple fields if we wanted to. In this case, we're just grouping by 1. This is like a group by statement in SQL or a pivot table in Excel. And then we're saying, okay, we're grouped by month number. What do we want to do from there? Well, in this case, we want to get the average, or Python refers to it as the mean. We're going to get the average of the average temperature variable. Now, similar to SQL and pivot tables in Excel, when you're aggregating that way, you can use count here. You can use sum, max, min. Keep in mind, all of those are only going to look at, consider non-null values. So it's, in this case, we're taking the mean across non-null values of average temperature, and we're grouping by month. And this is the result. We could run it just this way, but similar to before, this would not update anything. What we're doing in this case is we're doing that grouping exercise and we're taking the resulting data frame and we're calling it average temperatures by month. So we can reference this in the future. It actually exists. We've created a new pandas data frame object called average temperature by month. It has 12 rows, has 2 columns. There you go. So we can kind of clearly see here, July looks like it's the hottest month. It looks like the coldest month on average is January. All this is based on Raleigh, North Carolina between 1980 and 2022. Very interesting. We're going to rename some columns because ultimately we're going to merge this with our daily level table, the weather table. And so we want to give, by default, when we create that group by statement, it's just going to call, you can see the average temperature Fahrenheit. It calls it the same thing, average temperature Fahrenheit. Let's say we want to rename that column. We can use a rename statement using this kind of format. You can rename as many columns as you want here. You just have another comma, and similar to this, we have the text colon, the new name for it. In this case, we just want to rename one column, and we're going to change average temperature to monthly average temperature. And when we do that, you can see the name's changed here. And we just renamed that column. Now let's apply some math to a specific column. We're going back to the weather table. This is one row per day, 1980 to 2022. We're just going to get the mean of that. We could do .sum here, .count, all kinds of things that we can apply to this, but it's going to return a single value. It's taking the mean across all the different days in our weather data set. And what we find is that the average Raleigh, North Carolina temperature was 60.48 over that entire time period. Well, what we're going to do here is create a seasonal index, an average temperature index. We'll take our monthly average temperature, which is the value for that specific row in the average temperature by month data frame we just created, and we're going to take that average temperature, divide average temperature for that month, and divide by the average temperature period across all the months. And what that ends up doing is it tells us whether if it's below 1, it means that month is typically 67% colder, 67% lower temperature than the average day throughout the year across 1980 to 2022, 67% colder. And then in July, it's telling us that July is about 31% warmer than the typical day throughout the year. Very interesting. And you know, that's 79 divided by the 60 degrees that we saw. This would be 41 degrees divided by the 60 degrees we saw. Remember, this dot mean here, this was a constant. We saw what it equaled right up here. We were able to take the column that we just created, the monthly average temperature, the average temperature for that specific month, and divide by the overall average across all the days. And that's what got us to this average temperature index. Cool. I want to show you how to graph data in Python very briefly. Now, when it comes to visualization, building charts and graphs, if it's something really quick, maybe you build it in Excel. But generally, I'm going to recommend using an interactive dashboarding tool like Power BI or Tableau. You can filter in on things, you know, slice and dice things. That's what it's there for. But if you needed to do maybe some quick visualization, Python's got a lot of ways to do that, and it can often make sense to do that. Maybe you need to run some loops for documentation and show two variables against each other for a lot of different combinations of variables. Python, using its looping capability, which we'll take a look at, could be a great way to do that. So I'll show you very briefly how you can do that. We're going to reference the Pandas DataFrame name that we want to look at. In this case, average temperature by month, this new one that we just recently created. We're going to use the .plot function, and we'll specify what we want, what variable from that we want to have on our x-axis. So this month number is the one we'll specify, and which variable do we want plotted on the y-axis. In this case, we'll do the monthly average temperature. You can do a bar chart, a line chart, lots of other different types of chart. So you specify what kind of chart, kind equals. And in this case, I'm giving it a title. This is optional. I don't need to have this, but it wouldn't have a title if I deleted this. And there's all kinds of other things you can add. You can specify where you want the legend and how you want the axis formatted, all kinds of things. You could do a web search to figure those out. Or if you can't figure it out, feel free to leave a comment as well, and I'll try to help you out. And then we'll ultimately show this. And so let's watch what happens when we run this. We get a nice looking graph here that shows us by month what the average temperature is. You know, it's one thing to look at a table, and we can kind of see this if we look at it. It'd probably be even better if we didn't have all these decimals here. And there's a round function that we could use to get rid of those. But it's another thing to look at it visually. I always recommend making things more visual. And it's really clear that in the summertime it gets hotter. Imagine that. So that's our visualization. Now in analytics, oftentimes you can get value from just a single data set, but a lot of times the biggest value comes from when you combine data sets together. In this case, we've done some aggregation, but we want to take this seasonal index we've created and bring it back into our really granular by day weather data set. So in order to do that, we're going to use another pandas function called merge. So we reference PD, the alias we assigned to pandas, and we'll say dot merge, and we'll start with our left table. If you're familiar with SQL joining, this is really going to make a lot of sense. This would be your first table, maybe the one in your from statement. Weather, that's going to be our starting table. But what we want to do is left join into it the average temperature by month. And so that'd be the second table we reference here. And we're going to specify on what column we want to merge it together. In this case, we'll merge it on month number. And both data sets have a column called month number. The data set's the same. In fact, average temperature by month, we know we just created it. It was derived by grouping by month number. So we have that field in both data sets. That's what's going to determine how these are joined together. If you're used to Excel, VLOOKUP, XLOOKUP, HLOOKUP, all of those, it's kind of a similar concept where you're bringing in columns from other tables, but it's a little different in the way it works, in the sense that you can't create duplicated rows if a column matches on multiple things, like you can with SQL joining. So it's just a slightly different concept, but all of it's kind of a generally similar idea of, hey, we want to get some other columns from another table. We want to bring into the weather data set that average temperature index from the average temperature by month table, which is what you would use a VLOOKUP or an XLOOKUP or an HLOOKUP for in Excel, and what you would use different types of joins for in SQL. So you use the merge in pandas. We are merging on month number and how. Again, this is going to really make a lot of sense if you're used to using SQL. We're going to do an outer join. We probably go ahead and do an inner join. In this case, it doesn't matter. It doesn't matter because all 12 of the months that are an average temperature by month that we're merging on month number, all 12 of those months exist in both tables. The months that are in the weather, the month numbers that are in the weather table are the same month numbers that exist in average temperature by month. But if that's not the case, and you need to merge on something, then it starts to make a difference when you're doing a left join versus a right join, an inner join, or an outer join. And you can specify whatever type of join you'd like to do right here. So I won't go into different types of joins too much here. The idea is if you were doing a left join, it would keep all of the tables that are featured in the leftmost table, weather here. If you were doing a right join, it would keep all the rows from the average temperature by month table, regardless of whether they're in the weather table. If we do an inner join like we are here, it's only going to keep the values where the month number exists in both of these tables. And if we do an outer join, it would keep all the rows from either one as long as they're in one table or the other. So you can kind of think about inner as an and criteria for whether the month number, the thing you're joining on, exists in both tables. That's the only way it's going to be returned and included in the resulting data frame, which we're overwriting the weather data frame here with the result of this merge because we've named it. We could call it weather _2 if we wanted to be completely separate from the original weather data frame. And then so inner would be kind of like it has to be in both of those tables. Outer would be like it can be in either one of those tables as long as that row exists in one or the other. We want to include it in the results. And then left or right would be, hey, keep all the ones from the weather data set. Or right would be keep all the ones from the average temperature by month data set. And there's a lot of complexities there for left and right joining. We probably talk more about that in our upcoming SQL training session, so we can look forward to that. Another thing that could come up here is what if you wanted to join on multiple rows? You didn't just want to join on one row. SQL, that's really easy. You have an on statement, you can say on this equals this, and this equals this, and this equals this. You can have as many on statement criteria as you need. Very similar in Python in the pd.merge, maybe a little less flexible in the sense that it's always checking to see whether they're equal to each other. But you could do an on statement like this where you feed it a list of items. And if we merged on something, in this case, we would need date to exist in this field as well, or in the average temperature by month table as well. But if we wanted to join on multiple fields, we would just put them in a list, and basically our on statement could look something like this. And it could have as many comma separated strings here as you wanted to join on. So that's how you would join on, hey, I only want to merge these together if they match on both month, date, and month number, for instance. And not relevant for this example. This example, we're just merging on one thing, and that's month number. So we'll do that, and what you'll see here is now our weather data set. We have two more columns in it that we've brought in: monthly average temperature and our average temperature index. So we've brought in, notice that for a given month number, like January in this case, they all have the same average temperature index because it was joined in on month number. And so the average temperature index for January 1st is the same as January 2nd. And if we could see here, some other Januaries, like maybe January 1981, January 1982, and so forth, they would all have the same average temperature index as well because their value for month number was also 1. That's how merging works. Now, this is really where it starting to find some more interesting insights. So before, maybe we were able to see exactly how much colder December was, for instance. It's 27% colder, right? Or another 73% of the average temperature is another way of thinking about that. But that's interesting. But what we might want to do, remember, our original use case was to be able to say, how hot was this particular day or month relative to what we would normally expect for that time of year, right? Factoring in the fact, yeah, we know January is going to be colder, but factoring in what a typical January is like, how, was it a hotter day than normal or a colder day than normal? Factoring in the seasonality, the time of year we're in. So what we can do, this is the way you would deseasonalize anything. A lot of times you might be deseasonalizing sales, for instance, if there's a lot of seasonality in your business. You take that original variable, average temperature in this case, and you divide it by the index that we just brought in. And what that does is it creates a deseasonalized temperature. Watch what happens here for this particular day. January 1st, 1980, 37 degrees. Well, we look at what the average temperature index was there, and we know that January typically has 67% of the temperature, or another way of thinking about that is it's 33% colder than the typical day. So let's put that on a deseasonalized basis. That's a temperature of 56 degrees on a deseasonalized basis. And, I guess you'd have to compare, now you can kind of compare that from day to day here, and really be able to see whether a day, or we'll eventually group by month, was generally colder than another month when you after factoring in seasonality by creating this deseasonalized version. So one way of seeing this is, okay, 56 degrees or so. We saw that the average for this entire time period is 60 degrees. So that's one baseline we can use and say, that's still kind of a colder day. And you can see that here in the fact that, 37 degrees, but the typical for January is 41 degrees. So yeah, that's still a little cold for January, just slightly cold. It's going to be really volatile at the day level. So the next thing we're going to want to do is group by month. And this time we're going to group by the month start date. The difference from before, when we group by month number would group all of your Januaries, 1980, 1981, January 1982, all of those together. Remember, month start date, we just replaced the day with 1. And so what it's going to do is combine together all the days in a specific month in a specific year. So all the rows for January 1980, those 31 days, are going to be grouped together. And you can see that here, January 1980, February 1980. We're using the same group by function we used before. And in fact, we're using a lot of the same variables, but we've added a variable. So you can actually aggregate on 2 or 3 or more variables at the same time. We're getting not just the mean of average temperature, but also the mean of deseasonalized average temperature. And so we can see for the whole month of January 1980, The average temperature was 41 degrees, and the average deseasonalized temperature was 60 degrees. Very interesting. And now we can really compare this to February. February's deseasonalized temperature. And what we can kind of say here is January, relative to the following February, that following February was a colder February than normal compared to how cold that January was. The deseasonalized value actually, fell. From a raw perspective, we can see that it actually was colder. So maybe not too surprising there. Yeah, January to February it got colder. The deseasonalized temperature also gets colder, although a more severe drop there. We can really start to understand this perhaps when we start graphing it. So I'm going to graph this below. We're using that same dot plot. This time we're grouping by month start date, and we're graphing the deseasonalized temperature. Well, pretty volatile. We're looking at a lot of data points here from 1980, and we're looking at it on a monthly basis. Maybe looking on an annual basis could be okay. But if we looked on an annual basis, technically we wouldn't even need the deseasonalized temperature because all the years would have the same months included. So there wouldn't be a need to adjust it. This deseasonalized temperature maybe adds value when we're looking at things on a monthly basis because we know temperature can vary so much by month. Well, that was pretty volatile. So what we're going to do this time is filter down our data frame. Remember how you can take a data frame, do an open bracket, and then reference a column, in this case, the month start date from that same data frame, where it's greater than January 2018. So we'll have a lot less data points at this point. So we've created that. I'm displaying it below. And here I'm also going to just do the same graphing function here. We're taking the deseasonalized temperature and we're breaking that out by month start date, but now we're just doing it for this data frame that we filter down to 2018. Scroll to the bottom here to see what that looks like. Okay. We've got some movement here. What this tells us, looks like this is our first point, January 2018. That was, from a deseasonalized perspective, a cold January. Colder than some of these other months for sure, but then it was followed by a February that, compared to a normal February, was quite hot. And that came back down, it looks like, that following March. Let's look at the data table to try to understand this further. Here's that January 2018, that first data point we saw. Average raw temperature, unadjusted, 37 degrees. That's 55 degrees on a deseasonalized basis. Well, if we just look at that deseasonalized basis, we saw that it increased to 70 degrees in February. What happened there? Well, it went from 37 degrees to 51 degrees. That's a big jump, and clearly that is not the typical seasonal jump. It probably increases a little bit, and we could go back to our average temperature by month chart. I think it was maybe 40, 41 degrees is the typical change from, you might see like 3 or 4 degrees increase going from January to February. But this was a big increase in average temperature, and that's why your deseasonalized temperature goes up so much. Saying, yeah, that is a hot February. Maybe 52 degrees, but for February, that's hot. Then watch what happens. In raw terms, you're going to March, and as you can imagine, we could look back and see what happens in March. March is typically warming up a little bit more. But in this case, the temperature actually dropped relative to that really warm February. 52 degrees went down to about 47 degrees. So the temperature is actually dropping, even though we're getting more into spring here. This is very unusual. And the deseasonalized really calls that out. Okay, yeah, you're going from a deseasonalized perspective. That was a hot February, and now you're looking at a much colder March relative to most Marches, going all the way back down to 54 degrees, more in line with kind of how January was trending. You had a heat wave going on there. So that's the type of value that a deseasonalized temperature can add. You really clearly see that, yeah, that February stands out. Compared to a typical February, you had a much hotter February than you did a January or a March before that. All right, so we kind of went over this already where you can specifically, in this case, we're updating the data frame to say we just want these two columns and we can choose the order of them based on the order we include them in the double brackets here. So we're just filtering down our data set just to those two columns and we're switching the order here, similar to what we did before. I forgot to run this one, so notice how it says it's not defined. That probably means we haven't defined it yet. Now, you have to make sure you run each one of these sections. I think I've skipped over a few that we've gone over already. Didn't actually run them, so be sure to run each one of these code cells in that particular order. And if you ever run out or get an error about something not being defined, you can always start from the very top of the code and just rerun all those code cells. This is going to rearrange the columns as we saw before. Now, we've done a lot of different data manipulation and we've created this seasonal index. Maybe we want to write it to a table, right? So if we want to write it to a CSV file, there's a Pandas package called toCSV, and we'll just specify the argument here is what do you want to call it? Where do you want to put it? Well, we'll put it in the same path as the one that we imported that we set at the top in this case, but we're going to call it deseasonalized temperature. So it'll create a new CSV file in this case. Index equals false is something I generally include. It means that this index that we've been looking at when we display Pandas data frames won't be included. Generally want to include that. So you can go ahead and run that and it will simply save this Pandas data frame to this file path, CSV. If you wanted to create it as an Excel format, it would be a .xlsx file here. You would use toExcel instead of toCSV, and because an Excel file can have multiple worksheets, you would specify what the sheet name should be. And again, index equals false if you don't want it to include that index. Now, a lot of times, going back to how you import data, I would import data as a SQL query against a database. That's how I'd bring it into a Pandas data frame, do all this data manipulation, and then ultimately save the results of that back to a database, maybe a certain table that I'd have write access to. So I'd normally be writing this not to a CSV, not to an Excel file, but to a SQL table, maybe updating an existing one. All right, well, before we end our session today, I want to take you through some more advanced functionality. It's maybe hard to wrap your head around, at least it was for me, when I first heard about loops. But if you've used loops before, I'm going to show you how to use those. If not, I'm going to try to simplify it as much as possible because it can be really complex. Again, it was for me when I first learned about loops. The first thing we want to do here is create a list of items that we want to loop through. A lot of times a loop starts with that, is you've got to have a list of items you want to iterate through. In this case, I'm going to iterate through all 4 of our weather measures. And so I'm creating a list called items to loop through. It's a list, just like we defined a list before. Average temperature, precipitation, snow, average wind speed, all 4 of the columns that we have in our data set. And what I'm going to want to do is loop through those and do kind of the same thing, just referencing a different column each time. Loop is a great way to do that because the alternative is copying and pasting code and then replacing, find and replace. Okay, instead of average temperature, I want precipitation, and I'm going to copy and paste that, and instead of precipitation, I want snow this time. No, I mean, even if you did that one time, if you have to change something later, you've got to change it in multiple places. There's also the challenge of if you need to, your code being not as concise. So looping can help your code be more concise as well. So let's run this, and what you'll see is we've got a list. We've printed the list here. Here's our for loop. So a for loop starts with the word for, and then you give it a variable name, a temporary variable name. This can be anything, but you've got to be consistent with whatever you set here is what you need to reference later. In this case, we'll call it weather underscore type. For weather underscore type, and then another keyword and an end statement. So for this variable in, and then you would list whatever your list is. You could actually define the list here. I could put this list right here. In this case, I'm referencing the name of the list, the object name we gave it, items to loop through. and then it needs a colon after that. And indentation is really important here. There's something called an if statement here, and it also uses this indentation. But what we'll do here is indent, and we'll say within each of one of those loops, the first time it's going to be looping through where weather type equals average temperature. And the first thing it's going to do is print whatever weather type is. So the first thing it does is it prints average temperature. But then it's going to go through another time, and another time, and another time. And each time, the only thing that changes in that iteration is that the weather type variable is now set to precipitation in round 2. And then it's set to snow in round 3. And then it's set to average wind speed. It's the last item it's looping through. It's looping through all the items in the list. And the only thing that changes each loop is that whatever variable is set here, weather type, equals something different each time. And you'll see what ends up happening is it prints a different variable name each time. So that's what we're telling it to do. There you go. We've got each one of our variables printed. Now, obviously, we want to do a little more than that. I want to show you how this really could have been anything. I'm changing that to WT here, just an abbreviation for weather type. You can call this whatever you want to call it. What's important is that you be consistent. So now if every item we loop through in the list is going to be called WT when we loop through, then I'm not going to print weather type this time. I'm going to print WT. That's the variable name we've given it. So you just need to be consistent with whatever you decide to call it here. It's going to do the same thing. I'll show you how an if statement works here as well. It's maybe somewhat of a similar concept. It's kind of like the np.where statement that we looked at to define a pandas column, but on the Python broader level. So if we want an entire Python statement to be ran in a certain case and not others, the if and elif and else statement is really good. So we'll do if maybe 1, and when we another thing I should mention is when you want to check and see whether something is equal in Python uses a double equal sign to check for that. Less than, greater than signs, those are seen as the same. You can do a less than or equal to sign just like you would in other languages. But if you want to check and see whether things are exactly equal to each other, it uses a double equal sign. So I'm going to say if 1 equals 2, which is obviously not the case, it will never be the case, and then what's indented here is what would be ran. Print yes. Okay, so it doesn't print anything because that condition is not true. It just skipped right over it. Now, similar to what we did here with the indentation, what indentation kind of does is it says, okay, when you're on this item, do what's indented, and then whenever you get to the end of that indentation and things aren't indented anymore, if we had another line right here, this would not be part of the loop. It's it's telling it that part of the loop part has ended. Go to the next item, and when you get through all those items, then move on to the part below that's not indented anymore. With an if statement, it's similar. It says if this is true, then proceed to run this code. And then this is not related to that statement because it's been unindented now. So if I said print no, for instance, it's going to print the no because that's not part of this if statement. If I had this indented, then it's still part of this if statement, and neither one of them is going to run. Now, if this condition is true, 1 equals 1, then they both run. So that's an if statement. Now, you can also add elif statements, similar to like the nested np.where. I'll do, okay, if 1 equals 1, maybe we do if 1 equals 2, which would be false. And then I do another condition here. I'll do like if test equals test, then print no. So let's try that. I need a colon after it, just like we needed a colon for our for loop and for our if statement here. Okay, it printed no. Now watch what happens if I change this back to 1 equals 1. It only prints yes. It got to this condition and it says it's been satisfied, move on. Elif, which is short for else if, uh, it is only going to check this if a previous condition has not already been met. And you can have as many of these as you want. But as soon as one of these, either an if statement or a previous elif statement is true, it stops. And you can have a catch-all. So let's do something like this. Make these first two conditions false. We'll say 1 equals 2, test equals test 1. And then else wouldn't have a condition. It's just saying if none of the prior statements, the if or the elif statements before, if they were all false, then just go ahead and do what we have in this last statement. So I should make this something different, no 2. Then you get no 2. Yeah, this one was false, this one was false, and so it's moving on to this, and it's absolutely going to run this because it's an else statement. There's no criteria around it. It's a catch-all, in other words. If this had been true, like let's set it to test equals test. So the first thing's going to be not true. It'll skip over that. It'll go this line. This is true. It'll print no. It would not get to this point. It would never get to the else statement. And so it just print no without the no to. Just wanted to show you how to do the if logic there as well. Well, back to the for loop, somewhat similar concept where you have this colon and indentation, similar in that way at least. We're going to say for WT and range 10, this is a neat way where you can loop through a number of iterations. In this case, we're not going through a particular list, although what range 10 basically creates is a list from 0 to 10, not including 10, so 0 through 9. So what we'll do is for WT in range 10, each time, first time it loops through, it's going to be looping through for 0, then 1, then 2. And so when it prints on the first iteration, WT is equal to 0, it's going to print a 0. And then it loops through and it prints a 1 and 2 and all the way up to 9 in this case. So you can use range to loop through a certain number of times. All right. Well, another thing I'd like to show you before we really see how this can be applied to a real seasonality index is how to use the format statement. Here we're setting a variable called, it's a test variable, and it's going to be called temperature. It could be called anything over here, any text we want to display. And what we might want to do, in this case we're using print, is display a variable, a value here dynamically. So just a couple of things to point out here. First of all is when you're using format, the way to tell Python that you're going to be potentially substituting in a particular object's value within a string is to start that string before you even get to the quote part of it with an F. So F, we could do a double quote or just a single quote here, but I like especially when I'm working with this format feature, I like to use either a set of three double quotes or 3 single quotes. So in this case, 3 single quotes. And if you do that, you just need to end that string with the triple quotes. What that does is it says, you might see a double quote, you might see a single quote in the string. Don't stop, keep going. See that as text. Don't stop. This string does not end until you see another set, in this case, of 3 single quotes in a row. That's when you know that I'm done with my string. So I could include, I could include a quote here, I could include a comma here, and it'd be just fine because I've used triple quotes here. So what we're gonna do here is print variable equals, and then these curly brackets in conjunction with the fact that I have an F in front of the quotes, which tells us we're using format. It's telling it, hey, look for some curly brackets. And if you see curly brackets within the string, I want you to look within those curly brackets, and that's going to be the name of a variable. And what I want you to do is take whatever is actually in that variable, temperature in this case, because we set it to test variable to be equal to temperature here. I want you to substitute that in. So watch what happens when we run this. It prints. It doesn't print variable equals and then, open open curly bracket, test variable, close curly bracket, it prints variable equals temperature. And if we change this to temperature 1, it's going to print temperature 1. We don't have to change this line at all. So the format feature can be really neat. And what's kind of cool here too is you can actually set this to execute on something as well. So in this case, we're telling it variable equals temperature 1, right? And we're just printing it. Let's say we wanted this to be an exec statement. And this is going to tell it, take this string that's created, which we can see exactly what it is here. But we actually want to run this. Now this is going to create an error because we would need to have quotes around this. So I'm going to put, again, this is why we have triple quotes here. We can put something like double quotes within it, and it doesn't stop. It doesn't see that as the end of the text here. I could run this. Okay, nothing happened. We didn't tell it to print this time. Again, if I print it now, it's going to have those quotes in it that I just added, right? If you actually wanted to run that statement, we see what it looks like right here. If you actually wanted to have it run, then you'd use the exec statement instead. And at this point, it actually ran that statement that was printed below. Well, what would that do? Well, it would set a variable, called variable in this case, equal to temperature 1. Now, if I type the word variable just to see what's in that Python variable object, it equals temperature 1. It actually executed that. So that's what this exec does. We feed it some text and we tell Python, I actually want you to run this. And so that's the difference between just printing it versus actually running it. So here we were just printing that statement. It didn't do anything, just printed some text. When we put exec around it instead of print, it actually ran it, and you can see that because now variable has a value of temperature 1. Let's do one more kind of example looping case here. In this case, we're going back to that items to loop through. Remember, that's that list of the 4 items up here. We define this list right here. We're going to loop through that again, and we're actually going to use this format feature in the process. So this time, what we're doing is each time we loop through that, we're setting that particular item in the list. That's going to be what the value of weather type equals for that iteration. And what we'll do is we'll take that weather type and we're putting that into this format statement. Again, we call that out, that this is a variable to substitute in based on the fact that there's an F in front of the triple set of quotes here, and that we have a curly bracket around it. So that's what tells it this is a variable to insert here. And then this is just text. Everything else in the string is just text. So what ends up happening when we run this is it prints the first time variable equals, and it puts the average temperature in there. And then the next time it runs through and weather type equals precipitation, well, it prints variable equals precipitation. Hopefully that helps make this looping concept and this formatting concept make a little more sense. If you have any more questions on it, feel free to leave a question in the chat. All right, let's move on to where we actually bring everything together to really apply this to maybe a feasible use case. I'm resetting the list. You don't need to. We already set this list, but I'm creating the list of things to loop through here. And I'm gonna create a blank data frame right here before we even get into the loop. So we're using that pd.dataframe, that pandas. This is a function data frame. In this case, you can actually feed it. You can feed it columns. You can feed it values. Remember, this is actually the function we use to create quickly that manual data frame above. In this case, we're creating a completely blank data frame. The reason we have to do this is we're going to try to add to a data frame, and iteration 2, 3, 4, it'll be fine. There'll already be data that's been loaded there. But for that first iteration, when we try to load to a certain data frame, it's got to exist first. And so we're kind of making that exist. It's empty, doesn't have any rows, doesn't have any columns, but it exists. So I'm going to copy this here. I'm going to click plus. I'll move this code cell that I just created up here. And I'll show you what this data frame, what a blank data frame looks like. It it doesn't have any rows, doesn't have any columns, right? So it's blank, but it has to, we need to have something, kind of a placeholder there. So we're creating this Pandas data frame. What we're gonna do is we're gonna loop through each of these weather measures, and we're gonna create a seasonal index for each one of them. We're not gonna create it separately. We're not gonna copy and paste the code we created above. We've already done this for average temperature. We wanna do this for all 4 of these weather measures, maybe even more in the future. If we wanted to do this for even more, maybe the minimum, the low temperature, the high temperature, all kinds of other weather measures that you can get from the MediaStat package that I use to pull this, we would just add additional items to the list. But what we're going to do, our approach to creating a seasonal index is the same across all 4 of these variables. So this is a perfect list opportunity. Well, what we're going to do is similar to what we did when we were printing above. We're going to loop through each one of these 4 items. And each time we loop through, we're going to call that particular item, the first one, average temperature. That's going to be what the value of this weather measure is. All right, let's look at the first thing we do. We're using the group by function. It's just a great way to aggregate Pandas data frames as we saw above. We're going to go to the weather table and group by month number. We're going to do that regardless of which variable we're on. We always want to group by month number to create our seasonal index. That's how we start. Notice that the variable we take the mean of, though, is we're pointing to weather measure. What's that? Well, that's equal to whatever item we're on in the list. So when it goes through the first time for average temperature, it's going to be taking the mean of average temperature. And when it goes through the second time for precipitation, it's going to be taking the mean of precipitation, and you get the idea, snow and average wind speed and on and on. And it's going to put that into a data frame called dftemp. Then we are going to create, we're going to overwrite that value. Remember, this mean column will just equal that value. So when it goes through for average temperature, it's going to call that mean of average temperature. And so we're still pointing to average temperature if we're on average temperature by putting weather measure here. And again, if it's on the precipitation, if it's on the snow, it's going to equal precipitation or snow. We're updating that column with whatever it equaled, whatever that starting mean was for that particular month. And we're dividing by, here we go again, referencing the mean of that particular variable, whatever we are on in the loop, whatever weather measure currently equals in that iteration of the loop, dividing by that mean, which turns it into, if we're on temperature, 55 degrees to something like 0.95, if that's 95% of the typical temperature across all the months of the year. So we're creating that seasonal index here, and then we're renaming it to index. Now, why would we rename it here? Why is that needed? Well, remember at this point, with the first iteration of the loop, that variable is still called average temperature, and when it goes through for precipitation, it's going to be called precipitation. And so eventually we're going to try to vertically concatenate or union all these things together. That's going to mean that our seasonal index for average temperature is an average temperature column. Our precipitation one is in a whole separate column. We kind of want to stack these things where they should be in the same column. And so we're going to rename it if it's currently average temperature, we're going to call it index. If it's on precipitation in the loop, it's going to call it index. If it's on snow, it's going to call it index. They're all going to be, this seasonal index is going to be all in the same column called index with this rename part right here. But that brings up another point, which is, okay, if they're all in the same column, how are we going to know which rows pertain to average temperature seasonal index versus precipitation versus snow? Good point. Let's bring in another column, and let's call it weather measure, that's going to indicate, again, which weather measure we're on, which item is it on in the loop. So this is going to equal average temperature when it's looping through for average temperature. It's going to equal precipitation when it's looping through for precipitation. And then finally, we're ready to concatenate the result of that to df. df, that's what we created here as a placeholder. It was completely empty, as we can see up here. The first time it comes through for average temperature, it's going to create this table with 12 rows, 1 per month, and it's going to have a column for index that represents the seasonal index for temperature for that month. And it's going to have this weather measure that equals temperature that tells us these are temperature indexes, seasonal indexes. And we're taking that df temp that we've been creating within the loop and we're adding that to df. This is a concatenation. Imagine you're in Excel, you have two worksheets and you take the data from the rows and columns from one worksheet and you paste them right below the data, the rows and columns from the other worksheet. You're vertically stacking. If merge was horizontally bringing tables together, this is vertically stacking tables together. It's the equivalent of a union in SQL. And so we're stacking to it. And then when it comes through for precipitation, now df temp has 12 new rows that are specific to the seasonal index for precipitation. We're going to add those to df as well. Our df table is getting longer and longer. We should have a total of 48 rows because each one of these is going to have 12 rows each for each of the months. And we're ultimately going to display it here, so let's see how it looks. There you go, average temperature, first 12 rows, there's your index. Here's your precipitation index with the relevant numbers based on rain. Same, and you've got your month number indicators and on. There's your snow rows and your average wind speed rows. Now notice the index here kind of repeats. If we wanted to reset that so that it really starts with 0 and goes up consistently, we can just do a simple reset index. But before we do, if we wanted to sort a data frame, we haven't done that yet. All it is dot sort values, and then you feed it. In this case, I want to sort by two things. This is kind of how it works in Excel, an order by statement. The first thing is the primary thing. First and foremost, sort weather measure alphabetically. Alphabetically because ascending equals true. If we wanted to be descending by alphabetically, then we would do this false. And it's alphabetical as well because it's a text variable. And then we also have month number here, and it's going to sort by that secondarily. Within a weather measure, within temperature, sort by month number. So we've done that here. You'll see maybe a little bit difference of a sort. Yeah, now it has average wind speed next, and then precipitation, and then snow, alphabetically, right? And if we want it to be the opposite order, this first true or false corresponds to this first item we're sorting on, and we could just sort by one item, in which case we would remove that. But they correspond to each other. So the first true here, if I wanted it to be sorted in descending order, I'd say false, and that would correspond to weather measure. If I wanted month number to be sorted false, I would change the second one to false. Well, let's just see what happens if I do that. Okay, got an error here. Weather measure, okay. I don't know if I ran that. So let me go ahead and actually run that. There we go. Now hopefully this will work. Yes, now you see snow on top, then precipitation, then average wind speed, average temperature, and so forth. Now again, the indexes here, they start over because we've concatenated everything together. If we wanted to reset that index, we can just use this reset index, drop the original index. And now what you'll notice, instead of it repeating like it does here, it's just going to go all the way from 0 to 47, which is really 48 items because of the 0. Very cool. So what's neat about this is we didn't copy and paste the code up here. We just looped through and did the same thing for 4 different variables. We only had to write it one place. If we want to change our methodology for creating the seasonal index, we change it within the loop and that's it. We change it in one place and that's all. That's much more concise. Loops can really be effective, and that's a good reason to use Python, is for its looping capability. I've learned about this pivoting function in Pandas, which I think is pretty neat. There's this pivot table option. It's similar to maybe a pivot table in Excel. What we can do, and it's really good for a use case like this, where we might want to say, well, let's have a row for each measure. So our table right now is in kind of long and skinny format, which is great for dashboards where you've got by weather, by month, maybe even in some data sets you might have it split out by other things. here's the value grouped by all these things. I call that long and skinny format. Again, that's usually what you want your format in when you're importing it into Power BI or Tableau. But if we wanted to just kind of quickly get some insights and be able to compare our indexes across our different weather measures, the pivot table option here is pretty useful. So we're going against this data frame. We've called it DF. So we list what data frame we're looking at. Which values do we want to show within the body? Well, that's index. And then we'll add an index here, which is, I believe this can even have multiple fields if you wanted to. This would be the weather measure. This is what you want on your rows, essentially. And then what do you want across the top? What do you want your columns to be? Month number is the variable we want to split out there. And we could swap these, and that should be just fine as well. What we can do with this pivoted view, though, it's kind of neat. We can look at January and say, okay, typically the temperature is 67% of average, or another way of thinking about that is 33% colder in January. What's the wind speed like? Oh, we'll just go to the wind speed column below it for January. The wind speed is about 6% faster on average in January than the typical month. Precipitation looks like it's about 8% lower in January. And snow is about 7 times higher than it is in other months. And likewise, you can look at this. I did not realize how much rain we typically get in the summer months. Just didn't put that together, but I guess it works out with the higher heat, of course. No surprise there that the temperature's higher. There's also more rain to keep that grass cooled off. Really cool how that works. Well, that's it for our demo. Had a few things that I wanted to just kind of talk through. One is around troubleshooting. We kind of covered that already. We did an example of how you would troubleshoot and just do a web search. Whenever you run into an error, capture that error message, take out the part that is specific to your use case, and do a web search for it. Stack Overflow is usually a good result. I usually take the first accepted answer, start with that, and you're looking for something with some sample code. Bring that over, try it out, adapt that sample code, of course, to your use case. It might be using a different data frame name, different column names. You're going to want to update all of that, but the general syntax, the keywords and everything, that part is hopefully similar to what you're trying to do. Let's say you didn't know how to do something, right? Again, a great idea as you learn how to do different operations is to keep some kind of an organization mechanism. Maybe it's a Jupyter Notebook with all kinds of data manipulations. This Jupyter Notebook we're using now could be a great starting point when you're creating a new analysis. Maybe you have this open, and if you need to import a new CSV file, you quickly can copy the line from here. If you want to do a search here, it's very easy. Control F and search for CSV, and there you go. I found it. You could also create this in Excel with like one tab per operation, just like we've been talking about. But I recommend having a handy reference Jupyter Notebook or Excel file for those. But you're going to run into some things where you haven't done it yet. And so in a case like that, like for instance, let's say we wanted to create a running total by group. What I might do is try to search for as close of a term as possible to what you're looking to do, and you'll kind of figure out the way to phrase things over time and see what works better than others. What I would recommend, if you're using something related to a Pandas data table, which we've primarily been using Pandas data tables throughout today, is I'd recommend searching for Pandas instead of Python. So clearly you've got to include one or the other, because who knows whether you want to do this in SQL or Excel or some other tool. List the tool, but with Python, especially with what we've been doing, you want to use Pandas instead of Python, especially if it's something specific to a Pandas data frame you're trying to do. So in our case, maybe we want to do a a rolling total, a rolling sum, and I'll do like Pandas. So I'll type Pandas instead of Python. pandas, and let's say we want it grouped. We want to do that rolling sum and then for it to start over again at a certain point. Grouped, I guess you could call it rolling sum, cumulative sum, running total. I'll do running total here. And here's a Stack Overflow result. So I tend to go for those, and there's actually quite a few under here that you could check out. I'll start with the first one. Now it's going to start with what the question is, and you could look at that, but a lot of times I'll just skip to the accepted solution, and it's usually going to be the first one right here. And I've got some example, I want some example syntax, and it looks like I've got it right here. So I would probably start just by copying that. So let me do that here. And I've got my data frame here that would be probably a good starting point for this. So let's just show the data frame, okay, by weather measure, by month number. If I wanted to kind of create a cumulative sum of the index, which doesn't really make much sense of why we'd want to do that, but just as an example here, this is my starting point that I just got. Now, this line here means go to the next line. In this case, I'm going to put it on all the same line. But there's a group by here, so it looks like we're grouping by a certain thing. We saw that with the group by function as well. In this case, we only want to, actually, I think we want to group by both things, the weather measure and this month number. So I'll include both of those there. You need to update this to be whatever is relevant for you. Now you'll notice here they're referencing df. That's a very common name for a general Pandas data frame. If we wanted to apply this to the weather data frame, we gave it a name of weather. We want to update this df to be weather instead. We actually called what we're looking at now df, and so we don't need to change that. You'll probably find that to be the case if you generally use, especially if you're only using one data frame in your whole Jupyter Notebook, you call it df and you're looking at another example. So many examples online, especially if someone's giving you a solution, they'll just use df as the default for the data frame name. So in this case, we don't need to update our data frame name, but in a lot of cases, if you called it something else, we would update that. We definitely need to update the column names, that we're clearly using different column names. Day does not exist in our data frame, so we do need to update that part. Okay, we're going to do a cumulative sum here. That looks good. Everything else here seems to be pretty generic. It's nothing that needs to be updated for a use case. Let's just see what this does. And that's obviously part of troubleshooting and learning something too as well, is just seeing what happens. So we see the index, cool, and we see it's increasing every time. And we could go up and compare, for instance, and make sure, okay, there's that second, let's see here, snow, it might have reordered things here. Yeah, average, so it's reordered things here, but starting with average temperature. But let's check and see if like row 2 here, for instance, this 1.4 for average temperature should be 0.67 plus the 0.73. Yep, equals 1.4. So at least in that example, it seems to be doing a cumulative sum there. And then notice when it gets to a new category, it starts over, which is exactly what we want. So you want to find, do a web search, keep it generic, just and use pandas in the name if it's something related to pandas. We're dealing with a pandas data frame here. Search for it, and that first result, especially Stack Overflow. I'd start with the accepted solution. I get some sample code, adapt that sample code to your data frame, update things like data frame names, column names that are relevant for your use case. Run it, check it out. If it actually does run, it doesn't have an error. We talked about how to handle errors. You'd search for those error messages then, or you could just move on to the next article for what you're trying to do in the first place. But ultimately, check the results and see if it's doing what you expect it to do. That's a great way to get started troubleshooting. Okay, the last thing I want to show you before we actually exit out of our Jupyter Notebook here is how I actually created this weather data set in the first place. I needed to use the pandas function, the numpy function, the time function, which allows us to delay the processing of things, which we might want to do when we're using an API. I think I've used this in the past when I want to pull data from multiple cities. And that's something to consider here. What we're going to show below is how to pull weather just for Raleigh. What if you wanted to get it for other cities? That would be a great looping use case. So maybe you take a shot at that and leverage what we just learned about loops. I'm using some other packages here. These packages, I believe by default, when you install Anaconda, they're some of those common packages that are already installed on your machine. So we never had to install a single package today. But if you're going to run this code, especially with Mediostat and GeoPy, these probably are not packages that were included by default with Anaconda. It doesn't want to overload your computer and download every possible Python package. So I've got some comments here about how you could go about installing those. What I would do is click plus. I'll put this code cell above here, and I would do an exclamation point. What this does within Jupyter is it tells Jupyter to run this within the command line. Technically, you could also run this just straight from the command line, but this, you can actually run it within Jupyter, and we're going to actually install a package that wasn't installed by Anaconda. And we're going to go to the pip. It's a repository of Python packages. So we'll start with exclamation pip, and then the keyword install. And after that, you just include the name of the package. Usually, there are a few exceptions, and if you run into errors, you can do a search for how to install this package. But most of the time, it would just be the name of the package. Pip install Mediostat. And if I were to run this, it would try to install it. In this case, it should say that it's already installed for me. I don't think it hurts anything. Forgot the E there. So it said it couldn't find it. Now there's a few reasons for that. Sometimes you have to install it by a different name, which is a good use case for doing a search in that case. But in this case, I realized I misspelled it here. So it's Mediostat. I need to add an E in there. Again, I've already installed it. You only need to do this one time. If you reopen this in the future, if you have another Jupyter Notebook where you want to pull weather, you don't need to install it again. You install it one time, it's done, which is why our requirements already satisfied. If they weren't, sometimes it'll update some of your other Python packages that are installed to a certain version that works with whatever package you're downloading, you're installing. You've done this now, and so you don't need to do it again. And another one you'll probably need to download for this in order to get this to work would be GeoPy. That's another less popular Python package that's probably not installed with Anaconda. I've already done this, but in geocoders, it's referencing here a module within the GeoPy package. It's only bringing in the nominatum function from the geocoders module within the GeoPy package, and it's already satisfied here. But you'd run that again, get to the command line, go to the pip, the repository of packages, install is the keyword, and we're installing those two. And now I'm just going to get rid of this because I don't need to run this ever again. It's installed on my system. That's how you install a new package that didn't come with Anaconda, but that you need to use for something. Setting my paths here, again, I like to set parameters at the top of my code. If I want to change the starting year, the ending year, or the city, you can just change those things here. I don't have to change anything else. I just run it. If I want to get this for Greensboro, I can update it here and run. So it's really good to set parameters at the top of your code. You'll see we're turning that year into a specific date because ultimately this Mediostat package requires a start date and an end date. So I'm getting the first of that year. I'm using this date function to get the last of that year by taking that, basically building a date using this date time function, feeding it year, month, and day. Then I'm going to take whatever city this is, and see how I'm referencing city here, and I'm geocoding it using this GeoPy library. It's going to take that city and turn it into a set of latitude and longitude points. And that's ultimately what Mediostat requires, is a point, a latitude longitude point rather than a city. So I'm using GeoPy to get it from the city state to latitude longitude, and then I can run this function here where I say, okay, here's the place, which is a point, a latitude and longitude. Here's the start date, here's the end date, and you can actually get this by, I think, hour and all kinds of different frequencies, but I'm using the daily function from Mediostat. It takes in 3 arguments, this particular function, the place, the start date, the end date, and it's going to feed back ultimately by day the weather. And it has quite a few different weather variables. You can see all the different weather variables that it returns and information about them at this path here. But what I do eventually when it returns that data is I only grab these variables, the temperature, the precipitation, the snow, and the wind speed. So here I'm just filtering to the ones we use today. And I rename those, give them more intuitive names. Again, you can learn more about the specifics about each one of those variables at this website here. Usually for every package, there's good documentation where you can learn more about what things represent. And then I'm saving it to a CSV file. And that's the file that you downloaded from valuedrivenanalytics.com and that we've been using this whole session. I want to talk to you before we conclude about a couple of ways that you might use Python in practice. Python is a great tool, and again, it can be used for a lot of advanced data manipulation when it comes to pulling from APIs and looping. But you might be thinking a lot of that basic stuff that you did around data manipulation, merging tables together, filtering tables, creating new columns, I can do that really easily using point and click clicks in Excel. Why would I want to do that in Python or SQL? Well, the value lies in the fact that you can code all this out one time, and then when it needs to be refreshed on the latest data or on a similar use case, it's already coded out. You don't have to do a bunch of clicks, especially if you're refreshing data, like you might in Excel when you do those things. So it's all automated. Now, it's at this point, our Jupyter Notebook, you would have to run it, and you can run all those code cells at once. You can run all, and so that could be really easy. Imagine coding out your data manipulation using Python and then just coming in and clicking run all, and then it's suddenly done. You've imported, you've done all the data manipulation, you've exported, really speed things up just doing that. But you can do even better. What you would probably do next, if this needed to be conducted on a daily basis perhaps, is to use something like Windows Task Scheduler to schedule your code. So in Windows Task Scheduler, you can schedule a specific Python file, and now it's going to run every single day. One key thing to that with Windows Task Scheduler is it needs to be on a computer that's always on, or a server. You wouldn't want to put this on your regular laptop, because if you're not logged in that day, maybe you're on vacation or it's the weekend, and your computer's turned off, it's not going to run. A desktop computer might do okay, that as long as it's always on. But you want it on something that's always on, so that the scheduler is available to run that Python code. So scheduling your Python code would be the next step. And you might create something that's purely in Python. Maybe you even use Python to not just write it to Excel, but you can even use Python to format your Excel. And you could even use Python, maybe the last step in the process after doing the data manipulation, writing it to Excel, formatting the Excel. All this is happening in Python. There's some great Python libraries for formatting Excel workbooks. The last thing you might do is have Python send an email. And there's plenty of code available online for sending emails from Python as well, or even a text message. And that might be the last step. So now, if all of that was previously manually done, it's all been automated, and it's scheduled to run whatever basis it needs to be through Windows Task Scheduler. Another possibility for how you might use Python is you may actually use SQL to manipulate and build a data set and bring that into Python via SQL. Remember, that's one of the way you can import data into Python is via SQL. And then you might be using Python less for the automation capabilities, maybe more for the data science capabilities. You use sklearn or scikit-learn or stats models to build a regression model or machine learning model with the data you've brought in via SQL. And then you would probably write that back to a database, the modeled scores, for instance. You've built a model, maybe you've applied a model, and you now have some kind of a scored, it could be a prediction of some sort. You've written that to a table, and then you would pull from that table in an interactive dashboarding tool like Power BI or Tableau. Those, those tools can be great implementation vehicles for your model. You wouldn't pass on your Python code to an end user like a salesperson and say, here's your model scores, here's your Python notebook to open up. No, they need a way to interact with those, and an interactive visualization tool is a great way to do that. So again, you're writing SQL to bring in data, and we will actually show, and we're planning on showing in our next definitive guide to data analytics training session on SQL, how to write SQL code directly within Python. You bring in that data via SQL, build a data science model in Python. The last thing that would happen in Python would be to write that to a database, and that entire Python notebook that we just looked at, something like that, would be scheduled using something like Windows Task Scheduler. So it's going to run every day to always have the scores based on the latest data, and then that's going to and then you'd have a interactive dashboarding tool that's pulling from that database that Python updated, and that refresh of the interactive dashboard would be scheduled on a daily basis too, sometime after the Python process would have ran. So at the end of the day, your interactive dashboarding tool has the latest scores based on the latest data. So those are just a couple of examples of how you might use Python for a real project. I just talked through 2 examples of how you might apply your new Python knowledge to a specific business use case. And I mentioned, I think a couple times, about scheduling your Python code to run on a regular basis, maybe a daily basis, automatically. And I was gonna just stop there, but I feel like this concept of scheduling your Python job is too important not to cover. So I'm gonna go ahead and cover that now. In order to schedule a Python job, so you've done all the hard work of running it, now you want it to get to run, we're gonna use Task Scheduler. Now, you would want to schedule your job on a computer that is always on. So generally, that's not going to be your laptop. You close your laptop maybe overnight, and then if your job is scheduled in the morning, it's not going to run if your computer's not on. So you need it could work on a maybe desktop computer, but some kind of a remote server or desktop server would be ideal. A computer that's always on, because in order for the task to actually run, that computer that it's scheduled on needs to be on. So keep that in mind when you're thinking about where to schedule this. But I'll show you how to go through that process. The first thing you need to know is where Anaconda, when you installed it, where it installed the Python executor or the python.exe file. That's the file that behind the scenes, as we've been running our Jupyter Notebook, it's actually what's running your code behind the scenes. So Jupyter is kind of the interface where you're running code and you're seeing the results, but behind the scenes, whenever you run a query or whenever you run a code cell, it's going to be sending it to the Python executor, and then that's going to send the results back to Jupyter. So to find that path, there's a really easy way of doing that. I've got it right here toward the end of our Jupyter Notebook. You're going to import the sys package, and this is a package that comes with Anaconda, was downloaded with Anaconda by default, one of those really popular packages. And we're simply going to print sys dot, and we're going to pull from the sys package this executable function, and it will display the path to your python.exe file. I'll just do Shift Enter and I'll run that for myself. I'm going to copy the output here, this part right here. We'll use that in Task Scheduler. And let's go ahead, we're going to come back here in a little bit, but let's go ahead and actually get into Task Scheduler now. So to do that, and this is a Windows application, there's probably alternatives for Apple users and other users, but I'll go ahead and search here. There's quite a few ways of scheduling code in general, but Task Scheduler is a popular one, so I'll search for Task Scheduler. There it is. Click on that. And there's Task Scheduler. Now the very first thing that you'll want to do, I think mine has already selected this, but yours may not by default. In the top left, click on Task Scheduler Library so that you get this view that shows you all the tasks that are currently scheduled on your machine. And there could be some here that you've never seen before. Some of these are set up automatically. And so I've got that highlighted, and then I've got these tasks that are scheduled on my machine. We're going to click on Create Task, not Create Basic Task, but Create Task here. And we'll call this maybe Schedule Test. We can call it anything. In fact, what I might call it, we'll schedule this daily in our example, but you'll have the opportunity to schedule it on any recurring cadence. Daily schedule test, and if you name the project here, and I'd probably put daily there so that it's really easy to see that this is a task that's run daily. Now this is something you might have to play around with. First of all, I'm scheduling under my account. You might want to schedule this under a service account if you or your team has one, just in case your password is changing. Whenever your password changes, you may need to go in and change it here just by opening up the task and closing it again. And if you're out of office or something, it's probably better if your team has access. So consider setting this up under your service account, and you can do that here. Now this option, I usually run under run whether user is logged on or not. So I would recommend that option. If it doesn't work for you, if you have trouble with it, you could try it with run only when user is logged in, but this is generally the option you would run it with. And I'd also recommend run with highest privileges, trying that out if you get a certain error. So when we actually run this, you may get a 0 times 1 error. There's a couple things that can cause that. One, your paths could be off. We'll eventually set some paths to the Python executor, which we should have by running that code cell we just did in Jupyter. And then a path to the actual Jupyter Notebook or .py file that you're scheduling as well. So those paths, if they're off, if they don't exist, you'll get a 0 times 1 error. Or if there's some kind of a permissions error. And if you're getting a permissions error, what I'd recommend is kind of messing around with some of these options here. Another option as well is to just make sure that you have permission to the folder where these files are, where the Python executor is, and where the .py file is that you've created and you're trying to schedule. So those are a few things to look out for. For now, I'm just going to run when the user is logged in before we say okay. I'm going to move on to we have a few more tabs to update. I'll click on triggers. Click on new, and you can schedule a task up to every 5 minutes if you needed to. So that I've actually had use cases for that where you kind of constantly want Python to be checking for a response or checking for a request. And so you could do that up to every 5 minutes. Within 5 minutes, you notice that there's a new request, be able to process it, maybe send a reply back. That's one way of handling things like that are more real-time in nature. For our case, and for a lot of cases, we want to do some processing of data. We might do that after the database has been updated. And so one thing to think about as you're scheduling things here, let's say I schedule for 7 a.m. Note your time zone. So I'm on Eastern time zone. right now my computer's on Eastern time zone. Sometimes if you're using a remote server to schedule this, your remote server might be on a different time zone than you are. This is going to be scheduled based on the time zone of whatever you're scheduling it on. And so you can usually look at the bottom right and realize pretty quickly what time zone it's on. So that's important. And then you need to know what time does your data usually get updated at, that your Python process is going to be used. And you want to schedule this no sooner than that. Maybe give it a little bit of buffer time and then schedule your Python job to run so that by the time your Python job runs, the data that it might be using is already updated. And then from there, maybe one of the use cases we talked about, this might be updating a database that your Power BI dashboard then pulls and refreshes on. So you need to think about what time you're scheduling your Python code to run here. Think about how long your Python job takes to run, add that to it, maybe add some buffer time to that, and then that would be the time that you want to schedule your Power BI dashboard or Tableau dashboard refresh or anything that relies on the output of your Python script. So you need to think about the timeline and the dependencies in your process. Let's say we've done all that. We know the data that the Python job is going to use is going to be updated at 7 a.m. based on whatever time zone the computer that we're scheduling this on is based in. And so we schedule it to run daily, 7 a.m. It's enabled by default. We want that checked. Okay, and there's our schedule, 7 a.m. every day. And then we're going to actually tell Task Scheduler what to do at 7 a.m. every day by setting an action. I'll click on New here. This can be a little confusing. Program script, you might think, okay, that's going to be the path to the Python file that I want to schedule and kick off, right? Well, actually, what we're really doing is we're kicking off the Python executor to run. And then what we'll do is pass as an argument to that the specific file that we want, the Python code that we want it to run as an argument to that. So whenever you're scheduling a Python job, the program script you put here is always the same, and that is this path to the Python executor. So if you've scheduled a Python job, your first one already, and maybe this is your second or third or beyond Python job you're running, I would open a previous task in Task Scheduler and probably just copy this path from there. But here we can also get it from Jupyter like we just did, and there it is. Now here's where we're going to have to go back to Jupyter. We need to create a .py file here. And there's a few ways we can do that. First, I'll go back to our Jupyter file. Let's say we wanted to schedule this code right here. There's a lot of code here. This was created as a way to show you all kinds of data manipulations. I would do some cleaning up and boil it down to just what we need before I would try to schedule this in Task Scheduler. In fact, we had some errors in here that were intentionally created to show you what an error message looked like. We don't want errors in a scheduled Python process. So we're not going to schedule this particular Python code, although if we wanted to, the first step would be to export it as a .py file after cleaning up the errors and getting it to just the code we need, of course. So we get it in good shape, we test running it, of course, make sure it runs without errors in Jupyter, save it, and then we go to File, Download as .py. In Task Scheduler, when we run the Python executor, it needs to reference a .py file. Remember, our Jupyter Notebook is a .ipynb file, Jupyter Notebook file. It's great for interactively running code and seeing the results, but we can't actually schedule it, not directly anyway. And so we'd want to export it as a .py file first, and then we would point Task Scheduler, we would put back in this item right here, the argument would be that exported .py file. We're not going to do that in this case because we want to simplify the file. Again, there's errors in here. Let's just get it down to the code we need. So what I'm going to do is create a very, very quick Jupyter Notebook file, and we will export that to a .py file, and we'll schedule it in Task Scheduler and really try this out. So I'll go back to our main kind of Jupyter home screen here. I can navigate to another folder, whatever folder I want to create this Jupyter Notebook in, but I'll create it in the same folder here. I'll just do new Python 3 as we saw at the beginning of this video. I'll call this scheduled task test. All right, what do we need to do? Well, remember, when you're creating your first Python file yourself, you'll want to copy and paste a lot of code, and what we just went through is a great way to do that. So as an example, usually you start by importing some data. You could manually create the data, but most of the time we'd import it. So I'm just going to search this file. It's got a lot of sample code in it for import. Now, import is a Python keyword, so you're seeing a lot of cases where we're importing pandas and so forth. But here's an example of where we imported some data via CSV. Take that exact same file and we'll put that in our new file here that we're building. So we're going to import some weather data. Now notice it uses the pandas package, so we need to go ahead and import pandas as PD like we did here. And if we forgot to do that, let's just say we forgot to do that. Name PD is not defined. Okay, so we'd look at that and say, oh, it's a function reading from PD. Oh yeah, PD. We could go back here and see, oh yeah, I see there's PD right there. We need to import pandas, give it an alias of PD. All right, so if we run this, let's see if that runs. Path is not defined. Okay, so we saw that error before, I believe, with the capital P path. So we need to bring that over our path as well. And I'll set this for myself. And you can set this to the path it used in the other Jupyter Notebook as well, wherever you saved weather.csv. So for me, it's going to be this path. I'm just going to copy it. The R in front of the quotes here means that we don't have to worry about the backslashes, although we normally would, but the R tells it to see this string as literal and not consider the backslashes as escape characters as Python normally would. So we can just paste just the folder part, not the name of the file. We're addressing the name of the file right here. We actually embed that in the read CSV, just the way we've set it up here. And make sure I have I need a double quote to end that. All right, now let me run that. Okay, seems like it worked. No error message. We can test that out just by typing weather in a cell. Very good. Well, let's go ahead and just do a data manipulation. Of course, wouldn't be worth using Python for this in reality, but we're just doing a quick test here. Let's create a variable called test, an extra column that just always equals test. There we go. And now let's say that's all we wanted to do. Now we're ready to export it. So let's search for some export code here. And we could, of course, just search online if we wanted to export it in a specific way, but we've got some code here. Here's an example of how to export it to a CSV file. So we imported our weather CSV file. We added a test column in this row. The last thing we're going to do is now whenever you copy code, there's going to be some parts that you need to update. This part was the Pandas DataFrame that was used in our previous example. Now we need to update this to be the DataFrame name we're using now, which is currently weather. It also points to path, which we've set here, so that's good. We'll call this weather export. Run that. And I'll delete this for now. Just test this out, make sure it actually did what we wanted it to do. Hey, there's our weather export file right there. It was just created. And I'll just double click on that to take a quick look. Should have a test column at the end, I guess. And it does. So we've tested out our Jupyter Notebook. We feel really good about it. That's the first step before you try to schedule anything. You want to make sure it works in Jupyter. That's going to be the easiest place to troubleshoot errors. So we validated that it works, which is great. Now we're going to save this, and now we're going to go to File, Download as .py file. And whenever we want to change this file and update the version scheduled to be the latest version, we're also going to need to export it as a .py file again from Jupyter and overwrite the .py file that we just created. So let me go ahead and export that, copy that. I'm going to paste it in this folder. Now what you'll notice here is there's a Jupyter Notebook file. That's the one we've been working with in Jupyter. That's the .ipynb file. But Jupyter, when you export it as a .py file, is going to give it that exact same name with a .py. So that's right here, and that's the one we're going to actually schedule. So what I'll do here is I'm going to press Shift and then right click while holding down Shift, and it's going to give you this extra option, copy as path. That's going to make our life a little easier. Watch what happens if we click copy as path. So I did Shift and then right clicked on the file, copy as path. Let's go to task schedule, back to our task we were creating here, and in arguments just do Control V to paste it. What that did, that shift right click copy as path, is it puts quotes around our path, which we need. In this case, we need the quotes on the left and the right side of the text. Takes the path, of course, the folder path, and includes the file name as well with the extension. Everything we need to have this set up, and this is the path of the .py file, that exported .py file. That's what we need to schedule. And now I'll say OK here. We're good for our whole task. I'm going to say OK again. And now we're ready to run it. So at this point, it says the task is not yet ran. Now, if you ever need to, sometimes when you open up Task Scheduler, it'll reflect an old status, and you just click refresh to see the latest. So note that, just click refresh whenever you want to see latest statuses here. It's not necessarily automatically going to update in real time. You'll see it hasn't ran yet. It is scheduled at 7 a.m. tomorrow by default. Well, we want to see if it runs now. So what we can do is we can execute it right now. Before, we don't have to wait for 7 a.m. to see if this works. We can right click on it and click run. Another option is to highlight it like it is right now and click on run. Either way works. Let's go ahead and do that. Now what mine did is it was so quick, it just went away. It brought up a command line very briefly. Notice it still says it hasn't ran yet. This is why we need to click refresh now, and we'll see the latest status. Said it completed successfully. That's a good sign. But let's actually test whether the result changed. So if this really ran in this case, then our file should be updated. Our weather export file that it exports at the end of it, 412, it just ran. So that shows us that, yes, indeed, it actually ran. It was just 412, and it's updated. So that's great. Now what can happen here is sometimes it could have been error-free when you ran it in Jupyter, and occasionally when you run that .py file, very occasionally, there's something in Task Scheduler and when it gets exported as a .py file that just doesn't work the same. Maybe it's being ran under a different user that doesn't have the same permissions, all kinds of things that could happen. You usually don't run into this, but every now and then you may. So let's say the situation was, and again, this isn't a great example because this is something you would be able to tell within Jupyter, but let's say you tried to create a variable a that equals b, and of course we haven't set b yet, so this should generate an error, and if we run this, we see it's an error. But let's say it's one of these errors that doesn't come up when we run it in Jupyter, but maybe it's a permissions thing, and so it comes up later. Well, let's actually remember if we're going to update this file, we need to save it, and it's very common to forget to do this step, but save it and download as a .py file. There we go. So now it's been saved, and I'm going to want to downloads, and so I'm going to want to take that latest file, and I'll do Control V. It already exists here, so it's going to ask me if I want to replace it. So I would say yes, let's replace it. And now notice the time associated with that file has been updated. There we go. I don't need to change anything in Task Scheduler. It's still pointing to the same file. The fact that it's been overwritten doesn't impact its path because it has the same name here. And that's important. We would want it to have the same name because we wouldn't have to, if we needed to go to, we could, but we'd have to double click in this, and we could go into actions and update the path here. And you can always go in and edit it later. But we wouldn't want to have to do that, so we'd just keep the file name the same and overwrite that file would be the way where you don't have to go into this screen and update any paths if you ever did need to update the code behind that scheduled.py file. All right, so again, ran successfully when we tried it before. Well, let's try running it again. Okay, this command line came up very briefly. Still says successfully because we haven't refreshed it, but let's refresh it. 0 times 1. So that means that there was an error in the file, or could mean a lot of things, but most likely what it means here is that there was an error. Now we go to, let's just see what our actual exported file looks. Well, this is interesting. The timestamp updated for weather export. Why is that? Well, going back to our code here, that error came afterwards. So it actually was able to run through line 5 and it just errored out here. So that file still updated. But at this point, at least running it through Task Scheduler, we have no idea what caused that error. Not ideal. There's a way to get around that though. So I want to walk you through that now. What we can do is enhance our .py file so that it'll somehow tell us what that error message is, even when it's being ran in Task Scheduler. Let's go back to, really what we want to do is go back to our creating a weather seasonality index Jupyter Notebook here, and the very last code cell, I've got some code. It shows how to do a try except statement. Now a try except statement is like an if-then statement, where with an if-then statement there's if condition and then colon, and everything indented would be ran if that condition is true. Well, the equivalent with try except is it's going to try to run all of that code. It'll run it no matter what. It'll try to run it. And then in an if-then statement, and an if-else statement, there's an else after the if statement. Sometimes it says, okay, if that condition wasn't true, run everything else that's indented after the else statement. Well, with try except, the equivalent of that else statement is an except statement. Basically, it's going to try to run everything indented after the try block. But if as soon as it runs into an error, it'll stop running that code and it'll move on and run everything in the except block. If it never runs into an error, the except block will never be ran. So let's go over some examples here. In this case, print yes, print no will run just fine, but as soon as it gets to a equals b, it'll throw an error because b doesn't exist. We haven't set it yet. So let's just see that in action. All right, it ran yes, it ran no, and then it moved on to the except statement, and there's actually a print error message here. You can see it did indeed print an error message, and technically after it gets through the except statement, as long as there's no error in the except statement, it'll actually move on beyond that, and you see this print maybe here, it goes ahead and executes that as well. So that's try except statement where there's an error. If there is no error, like let's delete this line that would have the error, it doesn't print an error message. It never gets to the except statement. It just moves beyond it and it goes to print maybe. Now, what if we have our error, the a equals b, that error line before our print yes, before and no? Well, in this case, it never gets to the print yes, print no, because it runs into the error and it immediately stops, moves on to the except block. You can see it does print the error message because there was an error. It moves on to the except statement, and then it prints maybe at the end. It gets to this last line. So that's how a try except statement works. You can put anything in the try or the except blocks here. What we have in our except block here is we're grabbing the exception or the error, we're pulling out the line number, we're pulling out the error message, we're ultimately concatenating together with the plus signs here. That's a way you can take two object variables and concatenate them together, essentially the equivalent of a and sign in Excel. Put them together into another object variable error message, the concatenation of those things. You can see what that looks like here. It's printed on line 18. And then we're in 3 lines, these last 3 lines, we take that object variable and we simply save it to a .txt file that you could open with Notepad or another text editor. What's neat about this is technically the print here is great because there will be a terminal window that runs whenever the task kicks off the Python job, but it'll close when it runs into an error so quickly, or when it finishes so quickly that you probably won't even be able to see what it prints. But what we can do by saving it to this text file is actually open that text file and see the error message after the fact. There's no time when that would disappear. So let's go ahead, and I think we've already ran this, runs just fine. Let's apply this to our scheduled task test that we've been working with. So I'm going to start by selecting the first few lines here, and you can see it is necessary to import OS and sys. These are common packages that are installed with Anaconda. We end up using those in the except block here. I'm going to copy those and paste those first. Now, I should also mention that before you start to apply a try except block, this is something you might do at the end of creating your Python code. You want to make sure you have everything consolidated into one coding cell. And that's so that you can indent it all in a single try block. You can't really have a try statement that spans coding cells that I know of. If you know of a way, please leave a comment telling us how. So that means if maybe my code was spread across a few coding cells like this, my first step would be to consolidate them into one coding cell. You can still use spaces and comments. I should probably have some comments here, but we're just doing this to show the concept. So that being said, I will copy this first part, the packages that we need to import, and then what I'm going to do from there. So your code would normally not be indented like this. You would want to indent it all to say, this is the code I want you to try to run. It would be your entire Python job. And then after that, you would, for now, we can probably copy this entire except statement. And we've already set the path that this references here. That works out well. You could take your imports and your setting variables. If you really thought that they would not have an error, you could potentially put them outside of the try except statement. But now we have this set up. Let's go ahead and run it, see what happens here. Okay, print. So it moves on to the except statement and it prints it here. What should have happened now is it should have actually saved the error message to this error.txt file. Let's go back to our project folder, whatever you set as your path, and now you should see an error file there. Let's open it up. It says name B is not defined on line 12. Go back to our scheduled task, and there it is, line 12. There's our error message. So let's try this out in Task Scheduler now. Remember, every time we make a change to a Python job, a Jupyter Notebook, if we want it to reflect in our scheduled task in Task Scheduler, we need to save it. We need to download it as a .py file. All right. We need to go to our downloads folder where it would have been downloaded. I'm going to do Control X to cut that, and then I'm going to go back to the project folder, Control V to replace it. And this way we don't have to update our path in Task Scheduler. The file has just been updated. And now I'll go back to Task Scheduler. Again, last time it errored out. Let's see what happens this time. We'll run it. Okay, just finished. It says it completed successfully. Well, wait a minute, what's that all about? Let's go back to our Jupyter Notebook. The error line is still there, A equals B, and B hasn't been set. why would it say it's been completed successfully when there's a line that would generate an error? Well, this time we told it what to do in case of an error. We had an except statement, and as long as there was no error in the except statement, which can happen, if there was an error in the except statement, there would still be an error. You could actually set a try except statement within a try except statement to handle that error if you wanted to. But there was no error in the except statement, and so it ran just fine and says, well, it was an error, but you told me what to do in case of an error, so it wasn't really an error. And it ran successfully. Now, what we will be able to see in this case, and so that's why it's good for troubleshooting, is now when we go to our error txt file that we created, you can see it's been updated. We can open it and we can see exactly what error was ran, if there what was happened if there was one. In this case, it says name B is not defined. Notice it says line 18 here. Wait a minute, I thought it was line 11. Well, let's actually open up the file that's truly being scheduled. Remember, it's the exported.py file that's being scheduled in Windows Task Scheduler. Here it is right here. We can open this with a text editor. I'll open it. And we can see there's a few lines that have been added. These lines at a few spaces, a few lines at the top. This is essentially the code cell, a line representing the code cell here, and there's a few other things at the top. And so as a result, our lines have shifted a little bit. Now you can click on any line to kind of see where you are within the file. This is line 16, for instance, so I can, line 17, line 18. Line 18 is what the error message was pointing to, and there it is. A equals B got shifted a little bit when it was converted to a .py file. So when you're troubleshooting, compare that line number that would be in that text file you created to what's actually in the .py file, like we have here, and we've found it. Now we can troubleshoot from there. We have the error message and the line number. Let's see. So I think that covers the try except statement. But imagine, this worked really well for troubleshooting a file and making sure that it at least ran. Now we know what the issue is. We can correct it. We can, I guess the step at this point would be, all right, well, I guess we need to get rid of that line or set B if it's necessary, and then we could save it again. We can download as a .py file, and now we shouldn't get any errors, and we can test that. But what if you wanted to be alerted proactively if there's ever an error in the future? So the idea would be you get it set up where there's no error, you've validated that in Task Scheduler, but maybe the file disappears at some point and gets deleted, and now your process isn't updating. Do you need to go into Task Scheduler each day and check to make sure your process ran, or even check the txt file and make sure it wasn't updated, have another error message? No, that defeats the purpose of automation. What you could do in practice here is set yourself up to send an email in the except block. So if it runs into an error in the main part of the job, actually add some code here. You can find code online for sending an email through Python, or even a text message if you prefer that. And you could send yourself an email or text message, and even include the line number and the error message in that email. So you would be proactively notified anytime your job fails. So that's a great thing to do for any scheduled job, is to put everything in a try statement and add an except statement that sends you an email or a text. One of the biggest mistakes that analysts make when they're trying to learn a tool like Python is they watch too many training videos. You got to start somewhere. You've got to start with some good training videos, but very quickly I would recommend starting to apply that knowledge. And the biggest mistake a lot of analysts make is they never get to that stage where they're actually applying their knowledge. So here's one way that you could take what you've learned today and really apply it. Come up with an analysis use case. It could be one at work, or one just that a data set you're interested in. Maybe it's not weather, maybe it's the college football data set that we looked at in the Power BI training session, or any other data set of interest. And imagine taking that data set, you could pull it from a CSV file that you download or an Excel file you download, use the code that we went over today to start, and then adapt it to that particular file you're looking at and try to do some data manipulation on it. Ask some questions about the data and try to answer those questions with the filtering and the grouping capabilities and the looping capabilities that we've done today. See what you come up with, and just give an application a shot. You learn so much more when you actually try to apply these tools and watching training video after training video. So that would be my recommended next step, is identify a use case and pursue it. That's it for today's training series. If you like this video, please consider liking it formally and subscribing if you'd like to see even more analytics training videos in the future, especially our definitive guide to data analytics training series. Planning on having several videos on SQL, data science modeling. Both of those will be done in Python, along with some soft skills training. Please subscribe if you like alerts around that. And if you have any questions about today's training session, please consider leaving a comment and I'll do my best to answer it. Thanks again for watching, and now it's time to apply your new Python knowledge.